Good morning, good afternoon, everyone. All of a sudden, I don't know, maybe I need to have less things running. I saw the intro blip at the end. I was like, no! But good to see you here, Jacob. Good to see you here, John. Good to see you, Riley, Alexa, Elizabeth, Arden, Riley, and Cassandra right there. How's everyone doing this morning? Let me go off top, Chad. Does everyone have a good morning? Kendall, great to see you here. Newbot is now awake in the chat, so let's throw out some points. I got the hiccups. With that, I have fixed... Oh, you didn't see it yesterday. We had problems with the Stream Deck. Was not playing and doing things properly. We had to fix a whole bunch of stuff, but we got it fixed. I'm doing great, John. You're welcome, Emily. We're going to throw out some points. Ryan, great to see you here. And Calvin, good to see you here. Getting started. I'm out of coffee. Oh my God. One last drop of coffee. That's it. No more coffee. So I need to open a new box of Folgers Black Silk coffee. Good stuff, Folgers Black Silk. Make sure we got everything ready to go over here. Just doing a bunch of grade stuff and closing down things, getting everything ready to go. We're going to do as many topics as we can today. And what we're going to do is we're going to do a concept part of the topics, and then we're going to actually do some practice problems. So here's how this review is going to work. And please ask questions ask questions while we're doing it. Suggest topics. It's always driven by you. So what I want you to do is think of a concept that you want to review right now. Tell me what concept it is. Then we're going to go over it, and then we're going to do some practice problems on it. So it's always going to be in two parts. It's going to be conceptual and then practice problems. So we're going to learn the conceptual aspects of it, then we're going to practice it. And then we're going to do a new topic, learn the conceptual aspects, and then do practice problems. So you can name a chapter, you can name a part of a chapter, whatever you want. If you didn't know, there is Review 2. Ubot always here to help us out. But Review 2 has the link to the review material. So it's about to pop up there in chat. But it's all driven by you right here. I can come up with ideas, but what do you want to hear about? What topics are you interested in? Whether it be one sample T, two sample T, Z-test, the idea of testing in general, confidence intervals, one sample T confidence interval, one proportion interpretations. Alexa, good questions right there. Let me go take a look. Let's talk about those interpretations, and let's do interpretations for tests. So let's do that. Okay, so interpretations. Austin, good to see you here. So let's do interpretations for tests. Make Austin. Oh, wait. What? Oh, shoot. Oh, no. Mubot's no longer a mod. Woo! I accidentally demodded Mubot. I went to add Austin as a mod, and then I demodded Mubot. Mubot, you still okay, man? Hopefully that didn't destroy the channel or something. Okay, so let's do interpreting. We're going to do interpreting tests, concepts. Okay. So, and then we'll do interpreting tests, practice. Then we'll do interpreting intervals, concepts, interpreting intervals, practice. Okay, let me get jump going. But how's everyone doing this morning? People ask me how I'm doing. How are you doing? Getting jump going, getting everything going in the background right here, so we're good to go. But how are you doing? Cassandra, Riley, Austin, how's your morning going? Had any exams today? Any big plans for the weekend? Study? No, you can do more than study. You do have some fun. Relax. Life's not all about school. School's important. There's a lot of other things in life. With that, I think we're ready to go right here. So let's do this. Good, Leo. What's up, Leo? Always good to see you, Leo. 100 points for Leo right there. So let's do some interpretations right here. We are starting the first segment of the video right here with interpretations of tests. Let's head over to the main screen. Here we go. Now, we're going to start by interpreting tests, and we're going to talk about the concepts behind what we mean by interpreting tests. So, when we interpret a test, we need to know what is a statistical test. Let's start right here by talking about some statistical tests. And I'm basically going to do, I think, all the statistical tests you've seen. Here we go. Let's go and predict gender with broken a bone. Here, yes, we've done that a lot. Let's do if someone's in Greek life with how far they live from campus. And we'll put this one on the screen right over here. I'm going to disappear for a second after I put these all on the screen. And then we're going to go right here and go to analyze fit y by x. And we're going to predict if someone's, let's say, broken a bone by their high school GPA. No, I might actually have it. By, yeah, sure, high school GPA. Let's do it. Okay, so there's this one. And then we're going to go right here. Now take a moment as I put all this output on the screen. I want you to think what I'm showing you and the order in which I'm showing it to you. So, well, we might need just a little bit more. Analyze fit y by x. Distribution. Does anyone know everything I'm showing you right here? Can anyone name anything I'm showing you on the screen as I'm currently doing this, as I'm setting up our discussion on this topic? Can anyone name any of the things I'm showing you on the screen? Think about what I'm showing you and think about how it relates, because this is a little like tools and techniques. Who has any of the ideas? What am I showing you? What are these things right here? Let's see what the chat says. What does the chat say? Any ideas? No one said anything yet. Think about what this topic is. The topic is interpreting test results. So interpreting test results. So what do we have right here? Yo, Kaya, good to see you here. We're setting up our output right now, Kaya, to talk about interpreting test results. So what are we seeing right here? Slightly long hair. Slightly. Medium length. What do we see right here? Who knows what do we see? Anyone know what we're seeing? Can you tell me what Brian is creating for each thing? Oh, this might not fit on the screen so well. We do have a t-test on here. Where's the t-test at? Ooh, that's interesting. We do have a t-test. Okay. Almost in the order. Okay. So here's what we have on the screen right now currently. We have, and actually, you know what might work best? If we do the following. Let's screenshot it. And then let's bring over to a Word document. And let's take a look. Okay. Each of these, t-tests for Mr. Mean. So which of these are t-tests? Ooh, good question right here. Let's see which of these. Well, some of the output should make it a little bit obvious which of these are t-tests. So we have here the first thing we did ever, the second thing we did, the third thing we did, and now the fourth thing we did right here. Can you tell me what any of these are? Like, can you say like 3- is something this, 4- is something this, and then we'll talk about why it is that. So can you tell me about any of these things right here? What the first thing we did was, what the second thing we did was, and I'm going to write the variable names next to it. So while you're thinking about what these are, I'm going to write the variable names. This one was GPA. So the variable names are in blue right there. That one didn't highlight perfectly. Let's see here. 2 is a t-test. That is correct. 100 points right there. Sentiano, great job. 2 is a t-test. That is correct. 2 is a t-test. Now, why is 2 a t-test? How do you know 2 is a t-test? So number 2 is a t-test. So this was t-test. Number 2 is a t-test. Number 4 is chi-squared. Great job, Alex, right there. Number 4 is chi-squared. And 1, it is using, now this is tricky right here. We didn't learn it this way. I wish, so that is kind of correct. We do it via the z. So this is the 1 prop z. That's the 1 proportion z. And what is number 3? Did anyone get number 3 yet? What is number 3? So 2 was the t-test. And then think about why we call this one what it is. So think about what we call this one right here. Not the two-sided, very close, Kaya, very close. Not the two-sided, but the two-sample. The two-sample. The sidedness goes to the alternatives. Like when you think about sidedness of a test, that goes to which sides of the distribution are we shading. So you can do the does not equals alternative on many tests. And so the sidedness goes, oh no, you got it. Yeah, very close. It's the two sample t-tests because we have a yes and no sample group. So this is the two sample t-test. And the key right there is the two samples. So maybe I should highlight the two samples. You're taking two samples to kind of connect some wordings right there. So you have two groups you're comparing, why we call it two samples. So are there any questions about any of these tests and why you use them? Let's kind of talk about just the variables for a moment, then we're going to get to interpreting these results. But the variables you would use right here are, for the first one right here, you'd use a singular categorical variable. For this one, you'd use a singular quantitative variable. For this one right here, you'd use a quantitative y and a categorical x. And you can see this right here. It's a quant y and a categorical x. And then the chi-squared is what? What is the chi-squared? Which is the condition of chi-squared. So by knowing the chi-squared is this, you know a condition for it. The chi-squared is what? And these are all the tests. Categorical, which is count data. Great job, Alexa, right there. Chi-squared has the condition called count data, which is a categorical y and a categorical x. And this is really a cliff notes of every test we've done. So make sure you kind of know this as we go through this. We're going to look at the outputs right here and what the outputs mean, but understand that we tested GPA, which is a t-test. This is a quantitative variable, GPA is, and here's the t-test right here. This is mimicking the one proportion z-test we do. We do it by hand. It's for a categorical variable, like breaking a bone. This is the two sample t-test, which is a quantitative y, high school GPA is quantitative on the y-axis, and a categorical x that is two-level, breaking into two groups, i.e. two sample, and t-test because it's quantitative. Like GPA here was quantitative, it's still quantitative here. So we do a two sample t-test where there's two samples, two sample. I think sometimes you don't realize, it's like two groups that we're comparing to each other, two samples. And so now you see right here the categorical data does the chi-squared test of independence. I guess you could connect all the C's right there, but that's just coincidence. Oh, it's a little delay on that. Okay, so now we're going to start interpreting the results. So these are the tests we are doing, but now we're actually going to practice interpreting the results. And for this, I suggest using a structure. So put this on a note card. So let's get to our practice interpretation part of the review right here. And my biggest suggestion is, again, what? What should you do with what I'm about to do right now? Might be a big one. You might need a big one. Good to see you here tomorrow. What should you do? What should you be doing as I start this right here? What should you do? What should you have out right now? This is note card. Alexa got it right there. So remember, just me saying it helps, but if you say it, if you practice it, if you write it down, it's going to stick in your head a lot more. We all learn differently because we might learn by repeating it out loud, by thinking it, by writing it down, by teaching it to a friend. The more things you do to practice something in different ways, it's like a different exercise for your mind. That's how I exercise. So exercise better than Brian is the moral of the story. Anyways, well, let's start with I blank the null hypothesis. No. That Word knows what I'm writing. That this at the blank alpha level. This means I do. Oh wait, with a p-value of. We're doing everything. We're getting all the points. No grader's gonna. If a grader says you didn't get points, we're saying what? I wrote everything perfectly. Now be careful, people will make mistakes on this. So let's go right here. We need a little more space on this. And at the with the okay, this is a lot. It's probably one of the harder ones. Like this is a little bit harder than confidence interval testing because we're going to start right here with the following. And what do you think goes in this phrase? What do we do to the null hypothesis? This is good practice right here. What do we do to the null hypothesis? We only have two options right here. So what do we do to the null hypothesis? There's two options. So I probably go exactly right there, Kai and Alexa. We're going to say I either reject, or fail to reject. We're going to keep these in the order by which we use them, but those are the only two options you have right there. You either reject the null or you fail to reject the null. Reject the null when the p-value is what? Alpha. Reject the null when the p-value is what? Like, just, you have to have this just ingrained in your head. When the p-values, reject the null. When the p-value's lower than alpha. When the p-value is low, reject the null. When the p-value is low, reject the null. When the p-value is high, just let it fly. No worries, Samuel. You're here just to help us practice. Thank you, Samuel. When the p-value is low, reject the null. When the p-value is high, just let it fly. And 0.05 alpha is usually assumed. Great answers right there. Good practice. The null hypothesis that. Now, this is the tougher part. State your null. State what the null hypothesis is in words, and that's going to be a harder part for a lot of people, so we'll practice it here. Low means we have evidence. At the, so we'll state alpha level. So assumed 0.05, but check problem. Okay, so some problems might give you an alpha level. So unless otherwise stated, alpha, which is the what? What is alpha defined as? Think of it as a bar. Alpha is merely a bar that when p-value is what, we do what? So what's the point of alpha? This whole alpha thing is just saying, here's my standard. And if what? It's the threshold by which we reject. If the p-value is below this, not at this, if the p-value is below my alpha, usually 0.05 unless otherwise stated, I'm going to reject the null. And this right here is nice and easy. This is just p-value. So this is just p-value. That's all that is right there. It's just p-value. This means, and so how should we say this? Standards. We do have standards in statistics. We have alpha levels. So this means I what? If you can fill this in with me right here, if you know what the next parts we're going to use are, that's very good. That's good practice. So this means I what? What would be I do or do not have evidence, right? Yep, exactly. So right here, and great job right there, Alexa, doing great. So I do or do not have evidence. Notice how these go together right here. That if you reject the null, you do have evidence for the alternative. Does that make sense? Like the first option right here that you could go down on this choose your own adventure, not you don't get to choose it, but you follow the path, is to reject the null, and that means you do have evidence. If you fail to reject the null, which is do not reject, then you do not have evidence. So those are paired together as choices like I reject the null, I do have evidence for the alternative. Now this is the harder part once again here where you have to state your alternative. So state the alternative is a harder part. Okay, so the number one way to practice this is for me to choose one of these tests and to see how well you do. So you will hear me say the answer to every one of these tests, but we're going to do it one by one by one by one. There's 4 of them. And you need to try to interpret them. And if you can do a great interpretation, that'll show you you're on track. So let's start at the very beginning. A very good place to start. We started with, and we were talking about broken a bone right here. So let's see this test right here. Now the test is probably going to write out more information. And I'm going to show it right here. And let's say p-value. The p-value for the does not equals. P-value does not equals test, or does not equals alternative. So for prob greater than absolute value z, I wish it did the z, equal to 0.04. So now take a moment. First, it was for all the tests at the end. This is tests, and then we're gonna do confidence intervals next here, Alexa. This is for test interpretation, and then we're gonna do the test interpretations, and then we're gonna do confidence intervals interpretation. So we'll do confidence intervals next. So stay tuned for interpreting confidence intervals for each chapter coming up here next. So take a moment right here, try to fill this in. We're testing the true proportion of people who've broken a bone. So take a moment, try to fill it in, see what you get, see how well you do. If you're watching this, write this down at home or type it in the chat. Put it in the comments if you want. Add a comment to the video with the interpretations. Let's see if anyone does it later. What do we got? So we are testing broken a bone, right? We could use either one's fine. Let's use the have. We'll see what anyone says. So just look at your p-value to begin with. That's the easy portion. So think about the p-value with an alpha level assumed to be 0.05. What is the null hypothesis? We're testing whether or not people have broken a bone. So what would the null hypothesis be? My null hypothesis is that the what? So let's think this through. We're testing if people have broken a bone, right? So what is the null hypothesis? We have a hypothesized proportion. So the null hypothesis would be what? Keep asking questions or try to put some in the chat. Don't worry. Just ask questions. Put some in the chat. Don't worry. Take a chance. Take a leap of faith. You got this. Give it a moment or two more. So what is the null hypothesis? See, who's got the cart rolling? I'm going to give it a moment or two more, and then we'll start answering this. But kind of. Well, yeah, it kind of is. But written in classical sense, Kaya right there. Thank you so much. We're going to use, I guess I circled both of them. We're going to use this one right here. Here's the null hypothesis written out in statistical notation. So how does that read? What is the null hypothesis right here? The null hypothesis is the true proportion, finish the sentence. The true proportion what? The null hypothesis is the true proportion of what? The null hypothesis states that the true proportion, so read it right here. The null hypothesis states that the true proportion of people, what? Oh, we got some good stuff right here. Exactly, Kyra. For people with broken bones, 50%. Exactly. The true proportion of people for broken bones, 50%. I reject the null hypothesis that half of the proportion has broken a bone at the alpha level of, real quick, alpha level 0.05. Good work, Leo, right there. Alpha level 0.05 right here with a p-value of 0.04. So alpha level 0.05, I reject the null hypothesis at the alpha level 0.05 with a p-value of 0.04. No worries, right? That's why we practice. This means I do have evidence. So now remember, since you rejected the null, you do have evidence. So go down, remember right here, if we reject the null, that means we do have evidence. I'll highlight that in green. So you rejected the null, you do have evidence. And this is why we're practicing right here. I promise you, like, we're making sure everyone's going to get it right. So good practice for my alternative that the true proportion is not 50%. And it's not that more than, because we did the two-tailed test, the absolute value. Alexa wrote, I reject the null hypothesis that the hypothesized possibility of breaking a bone, or no, and so the true proportion, Alexa, because the null states that the truth is equal to the hypothesized value. So that value, this hypothesized value is right here. And the null hypothesis is that the true proportion of people who have broken a bone is 50%. Does that make sense, Alexa, right there? I reject the null hypothesis that the true proportion of people who have broken a bone is equal to 50% at the alpha level of 0.05 with a p-value of 0.04. So that's good right there. So everyone listening on the first part, try writing it down again just to practice. I reject the null hypothesis that the true proportion of people who have broken a bone is equal to 50% at the alpha level of 0.05. It says right here, and also we assume it, with a p-value of 0.04. Good question, Majed, right there. This is the absolute value right here, which is the two-tailed test. We'll see that more in output, and I think the test also tells you, I think it does, or it might show output like the t-test. The absolute value one does both sides, so it shades both sides, absolute value on both sides. So that's how we would know from this. Also, I wrote it down here in the alternative. Good questions, Majed, right there. So when it has absolute value signs, that is the does not equals. That is correct. The absolute value is the two-tailed test when you test greater than absolute value of wherever you landed on the curve. You're welcome, Ajed. Great. Keep asking those questions. That's what we're here to do. Like I want to make sure we get as many questions as we can, because if you're here asking questions, awesome. This means I do have evidence for my alternative that, and then the last part right there, the alternative that the true proportion of people who have broken a bone is not equal to 50%. Does that make sense? We do have evidence for the alternative. So we're going to try another one here. Are there questions on this one? Remember, we're just practicing interpretations. So try writing it down. Try practicing it. Let's see right here. The alternative was the true proportion of people who've broken a bone is not equal to 50%. I do reject the p-value being right here, the alpha level being right here. State the null. The true proportion of people who have broken a bone is 50%, and I reject the null. So those are the answers to the blanks right there. Let's try another one right here. What was the second test we learned? The second test, we're going to go talk to Mr. Who. What is the second test we learned? We're going to go look at the second test. There we go. Whoop. The second test we learned. The second test, the t-test. Mr. T is going to help us out with the t-test. Let's grab our t-test right here and see what we find for this. Here is our, oh my gosh, some news popping up, or go away. The t-test is right here. I'm going to grab all this right here. Let's test the greater than test. Okay. We're going to do the greater than alternative. The greater than alternative. So remember, I'm telling you we're going to test the greater than alternative. Okay. So there's our results over there on the side of the screen, and we need to interpret the greater than result. Are we looking at p-value 1, 2, or 3? We're going to do the greater than alternative. Great to see you, Santiano and Jacob. Are we doing p-value 1, 2, or 3, the greater than? Which it's, don't worry. Exactly, you got it. And notice how what we see right here, it's the greater than. Remember how we said absolute value is the two-tailed? So the way these look is, if you go right here, the first one is going to be the absolute value, which looks like this. And you can see it down there on the bottom. The greater than is going to be to the right of it, and the less than is going to be to the left of it. Now, an important thing to note is that these two p-values here add up to 1, and then this one is double the smallest. So you can see that right there, that this p-value right here is double this one. Does that make sense to people? That p-value up top right there, I'll zoom in on it, is double the smallest. That p-value right here and here, they are double of each other because it's a reflection. Ooh, what am I doing? Oh, my brain's not working today. The visuals showed me I was wrong. It's there, and it's there. There we go. There we go. There we go. I did have it mathematically correct. I didn't draw it accurately, though. I didn't see the t-statistic was negative, so we were on the left side of the curve, and the red line shows you where you landed. You can see it over here on this curve, and it would be right here on my curves, and so it is a reflection of this on the other side. So a little quick mini lecture there on p-values and how they're found, that you just shade less than the curve, greater than the less than where you landed, greater than where you landed, or reflect on both sides where you shaded on the lower side. So that's how the p-values are found. So we know which p-value we're working with for the greater than test. So we're testing the greater than alternative. It's the one that's been selected for us on this sort of interpretation. We don't really see the p-value down here because they think you probably wouldn't interpret it, but the p-value would be all the area above here, and that is equal to 79% of the curve being shaded in. So with that in mind, let's try to interpret it. Okay. What do you do right here? What do you do? Let's think about it. Give it a shot. We'll put a little chill music on right here. I feel like I should go and grab coffee real quick. I'll do it here maybe after this segment. But how are we going to do this? Look at the p-value. Give it a shot. Good to see you, Sophie. So just take a chance and try to interpret it. This is GPA, what we're testing. The context of this is GPA. The context of the problem is GPA. It's a t-test because GPA is quantitative. Mr. T is mean if you're doing drugs. So how would we interpret this? Well, if you're looking at the reject or fail to reject, we always look at the p-value. And you would assume, we'll do something interesting right here. We'll do an alpha. If you've already written it, don't worry. It's going to stay the same, but you just change what was alpha. Let's say it specifies an alpha of 0.10. that's going to be the point at which we reject, and we need to look and say, is our p-value higher or lower than alpha? And if it's lower, then we're in the rejection region. And if the p-value is higher, then we're in the fail to reject, which means you don't reject, but we say fail to reject in statistics. So the p-value is going to make the decision on this. So first thing you want to do for this first part right here, if you're stuck on this, how do I reject or fail to reject? You look at the p-value here and you say, this p-value right here, is it higher or lower than alpha? That p-value right there, is it higher or lower than alpha? We're going to fail to reject. Great job, Majed, right there. Excellent work, 100 points. You got it. So the first part is fail to reject. And then we have to state the null hypothesis. You see we have a hypothesized value. So now we're doing the null. So try to write this out. The null hypothesis for this, written in general terms, is that the null hypothesis is that the true mean is equal to the hypothesized value. This right here is, in notation, mu naught. And that value right there is thus mu naught. Like this is mu naught, that's mu naught right there. Like the true mean is equal to the hypothesized mean. And then the alternative we are using by virtue of this symbol right here is going to be the greater than. So the greater than alternative. Any thoughts on this? Oh, wait, Leo's got something and Alexa has it too. I failed to reject the null hypothesis that the real. I'll take that right there. You could say, I like true. I'd take real. If I'm grading that, you're fine, Leo. The true GPA is 3.8 at the 0.10 alpha level with a p-value of perfect. This means that I do not have evidence from my alternative that the true GPA is higher than or larger is fine, than 3.82. I would give that 100% Leo right there if I'm grading it. So great job. I failed to reject the null hypothesis that the true mean of people who have the true mean GPA right there, the true mean, I'd accept that too. You say the true mean of GPA is equal to 3.82 at the 0.10 alpha level with a p-value of 0.7916. This means I do not have evidence for the alternative and that the true mean is greater than this. Great work, Majed. And Alexa and Leo, I just want to give you a huge thank you for practicing. And any correction I make is just to have you get the most perfect of answers possible. So 1,000 points right there. So thank you, Alexa and Leo, practicing this right here. And Arden practicing too. Let's see what Arden said. I failed to reject the null hypothesis that the true mean of GPA is 3.82 at the 0.10 alpha level with a p-value of 0.7916. I do not have evidence from my alternative that the true mean of GPA is... Arden, that's worth another... Arden, I have no correction for that. No correction. That is A+ right there. So Leo and Alexa and Arden, great work. And any corrections I make are just to get us these perfect answers that hopefully I don't think any grader... Like, there's variation in graders, so we're giving them everything they want. We're giving the perfect answers, and we're knowing how to interpret these and where the results go. So Arden, great work right there. Epic answer. I love it. So any questions about this right now? I'm going to go over all the blanks right here with you and what they would be, and check out Arden's answer right there and other people's answers. But Arden just knocked a home run right there. Hopefully, we only have 200 characters for responses, so I think some people are trying to like maybe get that response in under the 200 characters. Okay, that's awesome. Yeah, and this is helping us remember, when do we reject the null? What is alpha? This is a great way to cover things right here with practicing interpretations. So and then we choose fail to reject. I fail to reject. Why do we fail to reject? Because the p-value is higher than alpha. So the p-value right here is going to be higher than alpha. So I fail to reject the null hypothesis that the true mean of GPA is 3.82 at the, and then we have a alpha level of 0.10. That's what the problem told us. At the alpha level of 0.10 with a p-value of 0.7916. This means, so we have to go to the second option here, I do not have evidence for the alternative that the true mean GPA is greater than, just say this right here, I do not have evidence for the alternative that the true mean of GPA is greater than 3.82. Great practice. I fail to reject the null hypothesis that the true mean of GPA is 3.82. I do not, at the 0.10 alpha level with a p-value of 0.7916, this means I do not have evidence for my alternative that the true mean of GPA is greater than 3.82. Good work. Now it's on to the what? Now we're not dealing with one mean to test. We're dealing with what? Now we're not dealing with one mean. Good to see your taking the voice all over. Now we're not dealing with one mean to test. We're dealing with what? Cat quant, we're dealing with two means. Now we're doing the two sample t-test. And when we say two sample, it's not that we have a mean and a hypothesized mean. It's we've taken two samples right here. So the two samples we're dealing with right now, the two samples, that's weird. Why is it? I don't understand. You just really want me to read the news, don't you? The two samples we're dealing with right here are going to be whether or not people have broken a bone in their GPA. Why did we select unless otherwise? So Majed, keep it up. That Majed, we're throwing you 1,000 points. Keep the questions coming today. The problem might say use an alpha level of this. So if the problem says use this alpha level, that's what you use. But in other words, what's up, Kenneth? This is regular Brian today. Unless otherwise stated, assume 0.05. Does that make sense to you? So if the problem doesn't say anything, what's alpha? If the problem doesn't say anything, what's alpha? If the problem doesn't say anything, what's alpha? Problem says nothing, what's alpha? Problem's just like, then it's 0.05. But if the problem says alpha equals 0.01, now what's alpha? So that's alpha symbol right there. Now the problem says this. So now what's alpha? So the problem now says this. So 0.01. Now it's 0.01. So assume 0.05, but check the problem. So that's why we say assume 0.05. But if the problem says otherwise, like if the problem says alpha is 0.01 there, okay, that's their standard. They're just saying, I have this standard. And you're like, okay, well, we'll use your standard for alpha. So assume 0.05 unless otherwise stated by the problem. So well, we can use that alpha. So that's how a problem would state it. They would either say alpha equal to this, or they'd use the symbol alpha equal to this. And that's just the alpha right there, a little alpha symbol. Here, I'll make it look a little bit better because I want my symbols to look like they are. They go right there. There's your alpha symbol. Okay, so now we have the output here. This is the two sample t-test. We're on to our third test. We just did the t-test. And we don't need that top output. Talk a little bit about this. Oh my gosh, what have we done? Okay, there we go. That's better. Okay. So now when you look at this output right here, you're welcome. Yeah, this is the goal of trying to understand this. The easiest way to write the null hypothesis for this, and this is broken a bone. We'll give the context above here. Broken bone. Broken a bone is the categorical variable, and GPA is the quantitative variable. And let's do the does not equals alternative. Is the does not equals the first, the second, or the third one? Is the does not equals the first, the second, or third one? The does not equals alternative. The does not equals alternative is that the first, the second, or the third? The first one, exactly. The does not equals alternative is the first one. It's the greater than absolute value. Excellent work right there. And so it's going to be these p-values here and here, which relate to this value right here. And that's the total area under the curve shaded on both sides. Once again, showing that if we double the smaller, we get the absolute value. And also the lower and the bottom ones add up to what? We are just repeating this endlessly. But these two ones I just shaded right there must add to what, up to what? Because you're shading above a line and you're shading below a line. Those two values we've just shaded add up to 1. And then the does not equals is double. So the two-sided, the two-tailed is the two sample. So some confusion can arise when we say two-sided or two sample. So Arden, good question right here. This is called the two sample t-test. And let me differentiate between this. We might even, well, it's okay. Listen on this. You ready? It's called the two sample t-test because there's y. It's called the two sample t-test. Why? Why is it called the two sample t-test? Just repeat this in your head. I know I've said it a lot today, but it's called the two sample t-test. Why? Because it's called two sample. And this is because we have two samples. We have a yes group we're sampling from and a no group. There's two samples. Now, the idea of two-sided goes to the sign of the what? The idea of two-sided goes to the sign of the what? The idea of two-sided goes to the, well, I could just put it down there. The idea of two-sided goes to the sign of the alternative. The idea of two-sided is a concept of the alternative, which can apply to other things, not just the two-sample t-test. You can do a two-sample t-test with a two-sided test. So the sidedness is the sign of the alternative. So take that note if you don't have it, that when we talk about is it a one-sided test or a two-sided test, like for example, if I were to use the p-value, where is it at? If I were to use this p-value right here, no, I meant that one actually. This top p-value, is that a two-sided test or a one-sided test? This top p-value, is that a two-sided test or a one-sided? Type 2 or 1 in the chat. That top one I'm pointing at right now, is that a two-sided or a one-sided? It's two-sided. It's the does not equal. So it's two-sided. It's what you're seeing here shaded. It's 41% of the curve. That's the two-sided. What really might help to see this is if I do it this way. Do you see how this is two-sided right here? And now we go to the low side. That's a one-sided test, and that's a one-sided test also. But this is the two-sided, where we shade both sides of the curve. We shade this side and the other side. So that's the idea of two sides are being shaded on the curve. But tell me this. How many means are there in this question? We're testing people's GPAs. So how many means are we tested? Great job right there, Leo. How many means are we testing right here? We're testing GPA. So we're testing GPA, so how many means are being tested? We're testing GPA, so how many means are being tested? 1, 2, 3. How many means we're testing GPA? 1. So that means this is a t-test, and this is the two-sided t-test. Does that make sense? And then to contrast that, here we are with how many means are being tested. How many means are being tested right here? We have a yes group, and it has a mean, and we have a no group, and it has a mean, and we're looking at the difference. So how many means are being tested here? 2 means are being tested. We have a yes group, which gets a mean, 2 samples, 2-sample t-test. And then if we do this alternative, which, are we doing that one? We are doing that one for this one. Now we have 2 means, so this would be a 2-sample, two-sided t-test. Does that make sense? The samples, the 2-sample part of it, the 2-sample t-test means there's 2 groups being tested, and then the two-sided means the alternative is the does not equals. So this p-value is relative to the 2-sample, two-sided test. So a 2-sample, two-sided test. Does that make sense? On what the twos mean in that sort of language. But let me know if you have any questions. That's what the 2-sample and the two-sided mean of it. Great work. So now let's look at this output right here. We see we are doing a 2-sample t-test, 2 groups, and we are doing the two-sided alternative right here. So when we look at this, we're using an alpha 0.01. So what would we say right here? What would we say? Well, we're testing the difference in GPAs between people who have broken a bone and not broken a bone. So what would we say right here? This is the 2-sample, two-sided test. Give it a moment. Remember, if you're typing in the chat, you're getting tons of practice. I'm going to read it off. Try writing it down, or just write down the answers people give afterwards. It's good practice. Wherever you're at, we try to meet you. If you have questions, let us know. If you take a shot at the question, give it a shot. But what do we see? So the reject and fail to reject are going to be decided by the p-value. We're only using this p-value right there. I'll show that, just that p-value. P-values are the prob greater than. P-values are probabilities. So this is the p-value. It's telling you the probability of a result that's greater than absolute value of t. It's just p-value. So those are the p-values right there. I failed to reject the null hypothesis that people who have broken a bone. Close. So this one, I'm going to write out the null for you, Leo. What are we testing between these groups? Kelvin might have it. I failed to reject the null hypothesis that the true mean of GPA of people who have broken a bone is the same as the true mean of people with GPA who have not broken a bone at the 0.01 alpha level with a p-value of 0.320. This means that I do not have a demonstrable alternative that the true mean GPA is different between those that are broken. Calvin, that is insane. That is amazing. We don't have the 1,000 points locked in anymore, but Kelvin, great work. This is probably one of the toughest ones, longest ones to interpret. And so let's show how Kelvin did that right here. Kelvin, great work, and Leo, great work too. That was a lot to write. Like I was like, that's a lot to write. Okay, so the easiest way to write the null hypothesis is to look at this up here. What are you testing between these two groups? You are testing the what between these two groups? You are testing the what between the two means. The true mean of people who have broken a bone and the true mean of people who have not broken a bone, because mu is true mean. And you're testing to see if it's the same. That is correct, because the null hypothesis is that if you take the mean of yes group and the mean of no group, the difference will be equal to 0. That's the null hypothesis. And the alternative would be that the mean of yes group minus the mean of no group, their difference, is not equal to 0. But should I go ahead and enter my points in? If you have all the points, you can. You can still bring up Discord. It's your call. You got until Sunday to enter in the points. Don't worry. No rush. No rush. I'm going to have to fix the column because I can't get it to do the 1.7. It's going out at 2 right now, so it says it's out at 2, but it's, I don't know. Maybe I'll figure out what to do with it. First time I've done it this way, and I literally have it out. Anyways, I'll deal with it. I'll figure it out. It's just not accurately showing the numbers, and it's out of 1.7. Canvas, I don't like you. Okay, so we have the null hypothesis that there is no difference between them because we're saying that if you subtract the true means, there is no difference. The alternative being the does not equals alternative. So the first step right here, and a lot of people figured that out, great work. So the more of this you know, these are tougher questions, especially this one. We are going to say, I fail to reject the null. Why are we failing to reject the null? Why are we failing to reject the null? I'm going to highlight in green the information we need right now. Why are we failing to reject the null? Why would someone go down the path of exactly right there? My p-values, it's higher than alpha. So I fail to reject the null. We've stated an alpha level in this question. Usually assume 0.05, but questions can say use this alpha level because the p-value does not equal to alpha. Yeah, and then Majed right there, because the p-value is at or higher than alpha, to be very technical. Majed, great questions and answers right there, because the p-value is, we would probably just say higher than alpha, but the question is, what if it's at alpha? You only reject when it's lower than. So in technicality, if it's right at alpha, which we don't usually do on the test, I'm not a big fan of that. If it's right at alpha, you would not reject the null. So you only reject the null for p-values below alpha. When the p-value is lower than alpha, at or above, fail to reject. So great work right there. Majed, you've been so many, we're throwing you 1,000 points also. Keep up the questions. You got this. So I failed to reject the null. And so I failed to reject the null hypothesis that there is no difference. So we're talking about the difference. Is no difference between the true mean of people's GPA who have broken a bone and who have not broken a bone. And that's why we say the difference is equal to 0, that there is no difference between these true means. And then we state our alpha level, at the 0.01 alpha level, with a p-value of this right here. This means, do I have evidence or do I not have evidence? Make sure to follow this path. When you fail to reject the null, do you have evidence for your alternative? I did not reject the null. I failed to reject it. I do or do not have evidence for my alternative. So I don't have evidence. I don't have evidence. I do not have evidence for my alternative that there is a difference between the true means, that they're not equal to 0, that the true difference between the means is not equal to 0. I said it 2 ways there. I'd probably state it for my alternative that the difference between the true mean of people who have broken a bone and those who have not is not equal to 0. So we don't have evidence for alternative. Correct. Good work. Let's point out a little bit about this output. We've been doing a lot of great practice right here. We kind of need that actually. If I were to blank out this value right here, how could you find this value? If I remove that value, who can solve that value with this output? I'm just trying to show you things we can do on the test. How would you solve that value? So you saw it just a second ago, but how would you solve that value right here? How could you solve that value right there? And let me show you the equation. The equation is a great job. Alexa right there knows the tricks already. The equation is y bar 1. Alexa's shown the answer. Check it out in the chat. 100 points, Alexa right there. Y bar 1 minus y bar 2 over s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. You do get the formula sheet. and that is equal to the t statistic. Well, when you look at this equation, what do you have? The top part is just the what? Just think about what tests we're doing. The top part, this is on the formula sheet, correct. The top part is just the what right there. The top part of that equation is just the what. Like if you had to describe the top part in words, it's just a difference, right? So this is a difference, and that's the difference. And the bottom part is known as the what? The bottom part of the equation, this right here, is known as the what? The bottom part is the standard error. Leo's already, that's the standard error right there. So if you take these numbers and divide them, you literally get the t ratio right here. So we've had a few people put the answers in the chat right there. It is 0.03925 divided by 0.02755, and that'll equal this right there. So that is literally the mathematics of it, is to just to divide those numbers. Just take those numbers right there, and you can just go 0.03295 divided by 0.02755, and there's the number right there, 1 point, and John carries some more decimals than we do. What about, there's a tougher one. If we were to remove this number right here. So that number right there, and yeah, it would be great if we were on to this next, but that number right there makes it harder. How would we get that number? Well, let's look at the information we're given right here. So we've removed that number, and how would we find it? And it might be a lot to write out, but I'll show you how to get it. That is the what of a confidence interval. That's the what of a confidence interval. So that is the what of a confidence interval. How would you describe that? You have to know what you're missing to find it. It's the lower bound, Leo. That's exactly what I would say. It's the lower bound. It's the bottom of a confidence interval. So let's think about this. What information do we currently have? Well, we're missing this. We don't know what this is, right? And we go here. What is the value in position 1 and the value in position 2? And then we'll find a value in position 3. What is the value in position 1 or 2? Who knows? Tell me any of the values I have blanked out right here. What are the values that are missing on the screen right here? Who knows any of those values? Let's see what people say. I think, yeah, maybe Leo, that might be it. 2 is the upper bound. Yep. 2 is the upper bound. So the upper bound of this is I'm going to do 3 decimals, 0.87. Good, you can still see it. And yep, Alexa, you're seeing it right there. I think people are seeing how to solve this. And the center of the interval is the difference, which is the estimate. We're going to round this to 3. So not quite 1 minus p. So this is means. Remember, this is means. So no p hat here, because p hat is categorical. 100 points are there. P hat is categorical sample proportion. This right here is actually y bar 1 minus y bar 2. That is the difference right here. So the center of this interval is the estimate, which is the difference. The full equation to find this interval by hand is y bar 1 minus y bar 2. The difference plus or minus the t with degrees of freedom, square root, standard error, standard deviation 1, squared, that is correct, over n sub 1 plus s sub 2 squared over n sub 2. And so that's the full equation right there. And I think Leo is finding for us what? Because the thing in blank 3 right there is the margin of error. This is the plus or minus on the interval. We need to go plus this amount and minus this amount. So it's symmetric around it, and I think Leo's found it. By taking the difference between these numbers right here, we can find the margin of error. So the margin of error right here is just subtracting those numbers. Leo's got it in the chat right there. We're just going to take 0.087 minus 0.033, and the margin of error is 0.054. So it's just part after correct. This right here is the margin of error. Great job right there, Kaya. That is the margin of error, which includes the t and the standard error. The margin of error is everything after the plus or minus, so it's down here in the interval. and it's just how far away the center is from the upper and the center is from the lower, and it's symmetric, 0.054. So now we're just one step away from finding the answer. At this point, I hope people can find the answer. See if you can figure out the answer to what the lower bound of the interval is. Now, remember, we did a little bit of rounding right here. It should basically be this, but how do we find out the lower bound of the interval now? Now that we know the margin of error, this becomes a simpler problem to figure out the... this was a multi-step problem. We right out right here. What is going to be the lower bound on the interval now? So try to do it. I think Leo's found it right there, and we're just going to take and subtract. Great job, Leo, right there. We're going to subtract this number. And there we go right there, exactly. And so that becomes the lower bound. We're just going to take the center of the interval and subtract the lower bound, and there it is right there, negative 0.021. And there it is. Boom! Great job. Excellent work. And so we rounded our decimals a little bit, but that was a good practice solving, knowing some concepts about intervals, margins of errors, standard errors, all this good stuff right here. Now, you know what's... Oh, nah. I don't... Let me see. Where's it at? Yeah, basically. I don't know. I don't want to go too in-depth. I want to stay focused on the test. Okay, so now we're going to do the interpretation of the chi-squared output. So let's get some chi-squared output interpretation going on here. We're going to play this one. Okay, the last test to talk about is the chi-squared. When do we use chi-squared? We're throwing in as much review as we can while we're doing this. When do we do chi-squared? Leo's already got it in the chat for count data, which is categorical, chi-squared right there, categorical data. We're going to see mosaic plots, contingency tables, all that good stuff. 2 categorical variables, condition 4, count data. That is correct. So here's your chi-squared test of independence. Ooh, we're looking at people involved in Greek life. So we got, how far are you from campus? And then we have, are you involved in Greek life? I'm actually going to do something with this data really quick. I'm going to make it ordinal. Because we're going to see something. Yep. That's what I thought. Okay. Let's take a look at this. There's the result, and we're going to bring in the graphic. So we're looking at how far people live from campus and if they're involved with Greek life. We've got a lot of output for this. There's the test itself. That's the actual test right there. The prob, remember probs are p-values. And then we want to get just a little bit of extra output right here. We can grab the table, which is going to be kind of neat. Grab contingency table right here so we remember what it is. Oh, really? And I marked on my output. And drop this in. And last but not least, let's go grab that mosaic plot. Where is it? It's on mosaic plot. Here we go. Okay, this is the output you would see for chi-squared tests. That's kind of all right. Can't get past it now. Did it. I want this down here. Okay. What is it? Oh, nice. Leo already got the degrees of freedom on it. Great job, Leo, on the degrees of freedom. Okay. Let's assume regular old alpha right here. We're ready to go on this. We got the example up and going. So when we do the chi-squared test of independence, the very first and easiest thing I like for people to remember is to find the null hypothesis. What is the easiest way to find the null? If you've watched any of my videos where we find the null hypothesis for this, what is the first thing you should do when you get the chi-squared to write the null? What do we do? I'm ready to do it. And if you've practiced this, if you see the chi-squared that you're doing, you just need to put one word between them. And what do we do right here? And then we try to make a sentence from it. So what do we do right here? To write the null hypothesis for the chi-squared test of independence, which is our starting initial belief about any sort of test that we don't need evidence for, it's just our initial belief. We write one word between them. And I write right here, independent. Great job, Alexa, right there. We write independent. So this right here, Greek life is independent for the distance from someone is from campus. Exactly. Someone's involvement in Greek life is independent. So that means right there, Rock always knows. It doesn't matter. It doesn't matter how far you are from campus. Your involvement in Greek life would be about the same. We're going to find out more in just a moment here if there's evidence that they're not independent. As in maybe people who live closer to campus are more likely to be involved in Greek life, and people who are further away are less likely to be involved. Whoa, it's kind of what we see right there. So we know the null hypothesis is that someone's involvement in Greek life is independent of how far they are from campus. The alternative is just to put the word not here. Someone's involvement, so this is the alternative. Read the full thing. The alternative is the full thing, but the null hypothesis is just the beginning. Null hypothesis is that the two are independent. You could say dependent. You can say, and that's fine. Kai right there, 100 points. That is correct. Independent and dependent are complements. I like to use not, just because we could say like they're not equal to, like it's equal or not equal. And then Greek life is not independent of the distance someone is from campus. That means there would be an association. Majed, great work there too. That's the way I prefer to say the alternative. The null hypothesis is that they're independent. The alternative is that they're not independent. And that way it's like you start off by saying, this is what I think, but maybe I'm wrong and it's not this. That's my favorite way to do it, but dependent is quite a good way. Or you can say they're associated as an alternative. So the same word right here would be to say they are associated. So that's color coding right there, so you can see what goes with, really? Oh, look at that magic. Associated. That's the same thing as saying not independent. So it's synonymous, like they are associated. Someone's distance from campus is associated with them being in Greek life. So we're back here to the test now. So take a moment and see if you can do the null hypothesis. You can interpret the test result here. Now, a good thing to remember is the Pearson has your p-value. That's just memorization, but the Pearson has your p-value. The Pearson has your p-value. So if you're looking to say, well, which one of those do we do, the likelihood or the Pearson? Well, you go to my Pearson for your material. The Pearson has your p-value. It's just the name of the test we do is the Pearson chi-squared test of independence. So the Pearson is the one we are using, and it's just memorization that we are doing the chi-squared test of independence via the Pearson way of doing it. But what interpretations do we have right here? Let's take a second. Remember, the more you interpret it, the better. So take a moment to practice this, interpret this. It's going to jam out to some music right here. We're doing confidence interval interpretation next. We've done a lot of review of stuff, but probably a quicker segment on that. But this is really good interpretation stuff right here. Eat cup 2 of coffee. I reject the null hypothesis that Greek life is independent of the distance someone is from campus at the 0.05 alpha level with a p-value of 0.01. Yeah, Alexa, that's, yeah. I think when you finish off the sentence, you'll have it. This means I do have evidence for my alternative that Greek life is not independent of the distance from campus. Yeah, Alexa, you got it. And Majed's writing out the null alternative. I think that's correct, Majed. Have project 2s looked all right? Pretty good. They've looked pretty good. Pretty good. Please let me know. Graders can be a little harsh. I have given points back to like 5 or 6 people. You're always free to email me. I might say yes or no. You never know. If you want to email, let me know. I'm always trying to make sure I'm up to date on emails. One time someone emailed me. They were like, I haven't heard from you in 8 hours. And I was like, I've been teaching. I didn't say that. I was like, I'm sorry. I was like, okay. We'll see if we get a few more answers right here, but I'll read off the answer in a moment. Once again, to do this, we state to start, I either reject or fail to reject the null, right, Kenneth? Haven't heard from you in 8 hours. I think it was they emailed me at like 10 a.m. and then they emailed me at like 6 p.m. But like Tuesday, Thursdays are my busy day. This was a few semesters ago. And I was in like my office and doing stuff and meeting with students and teaching. And so they emailed me in the morning and then it was like 6 p.m. or something. And I saw the email and they had replied. Some grades have been released. Graders are trying to keep up to date. They have until Monday I asked them if they could get it done today, but some grades have been released. Check out the Discord. A lot of people talking about it. People saying like, mine got graded. I reject the null hypothesis that involvement in Greek life is independent of someone's distance from campus at the 0.05 alpha level with a p-value of 0.0001. This means I do have evidence for my alternative that they are not that, and probably stated fully, like if you have a little bit of extra room to write, for my alternative that Greek life is not independent of someone's distance from campus. Exactly. Well, then I get nice compliments from students too. Like I'll email back a student at like 1:30 a.m. They'll be like, "Whoa, I didn't know you were awake." And I'm like, I try to keep the email inbox at 0. I try to. It's tough, but I try my best. And I had a student be like, "Whoa, you're awake at 1 a.m." And I'm like, I'm awake at all times. Coffee. But yeah, no, I get more nice compliments than I do mean things. Every once in a while there's a mean thing. I'll take it. Okay, so how do we do this? Enough stories of Brian right here. No, thank you, Kai. Of course. If I see it, I'm gonna try to email back as quickly as I can. I reject the Majed got this. I reject the null hypothesis that Greek life is independent of someone's distance from campus at the alpha level 0.05 with a p-value of 0.01. This means I do have evidence for my alternative that Greek life is not independent of distance from campus. Majed, another 1,000 points. We're just going crazy on the points. Majed, I want to say huge shout out right there. Are you feeling a lot more comfortable with writing this and practicing this? You are doing exactly what we need to do. Majed, that would be, if I'm grading that, full points right there. I can't see any errors in it. Exactly. Great work. I reject the null hypothesis. Why did they reject? Because the p-value right here is well below the alpha level. It just has to be below. I reject the null hypothesis. And the null hypothesis is that the two are independent. Remember, we said the null hypothesis is that they're independent. Awesome. And then we assume 0.05 unless otherwise stated at the 0.05 alpha level with a p-value of, we state our p-value. This means I do have evidence for my alternative and the state the alternative that they are not associated. Exactly. And so now we're going to talk about the other output here for a little bit. Let's go over here and talk about this output right here. And let's say if you were to find, let's say, expected values. Now, you are given these values on the test. So we're going to talk about expected values. The expected values are row total times column total over grand total. So exactly RT times C. Exactly, that's the way I usually do it abbreviated. That's great right there, Kai. More points. That's exactly the way I usually do it in abbreviated writing. RT times CT over GT. And so when we think about this right here, let's find the expected cell count. So this leads to an expected value. Let's find an expected cell count value for, let's say, this one. So how would we find the expected amount for that cell right there? How would we find it? Take a moment, and then you'll see how, like, oh, it kind of works for that. So remember, we need to find the row total for it. We need to find the column total for it. And then we need to find the grand total. So the best way to do it is to realize you're just kind of lining up right here like this. You're just lining up across the cell. It looks like, oh my gosh, whoa. I did not mean, and the formulas will be given. That's so, why am I saying, wow, that's interesting? Why am I saying, wow? What's interesting about this? What is so interesting about this expected cell count? And I chose this one for a reason. So you can actually just circle the numbers that point in on it, row total, and you times those together, and then you divide by this. So you can actually circle the numbers. It's barely greater than 5. This was just pure coincidence. So, and it's less than 2. Well, but no, that's how many we observe there. So we observe 2. These are the observed counts. Although jump says counts are the observed. We'll use those in a moment right here. That is the observed value. Does that make sense? The counts are what we observe. We saw 2 people who are a 30+ minute drive who are in Greek life. Those are the observed values. Those are the observed. We expect 5.0002 or so. So 14 times 2.288. So we expect 5.0002. Exactly, and that's their difference. And the chi-squared is going to be, is it 1.88888888? Wait. No, it's going to be 1.8. Find the chi-squared now for this. So now that we know the observed for this, excuse me, the expected, now that we know the expected for this is equal to 5. We're just going to call it, yeah, we got to call it 5.002. And then we'll do a few more of these, and we'll see how we found these. We're just going to do more practice. Find the cell chi-squared of this. So now find the cell chi-squared. I think it's 1.8. Find the cell chi-squared now. Cell chi-squared is going to be, so trying to make sure I don't block what I'm writing. I want it to be big, but I don't want to block it. The cell chi-squared of a cell is equal to observed minus expected squared over expected. Okay, so what do we need? We just found the expected. So we know expected is this. Oh, wait. Yeah, that's right. It's 1.8, right? Confirm my answer of 1.8. Who's got the answer? Terry's 100% right. It's 1.82. Great job, Terry, right there. 100 points, Terry, in the chat. So we've highlighted the values right here. We just found the expected, and we go observed minus expected. So we're going to subtract off what we see right here. We're going to square that, and then we're going to divide by the expected 5.002, and it is 1.8. That is a cell chi-squared. That is a cell chi-squared. Now, what do we do with the cell chi-squareds? This is a key concept. What do we do with these cell chi-squareds? You see that one we just found a 1.8? Every cell gets a cell chi-squared. You get a cell chi-squared. You get a cell chi-squared. So what do we do with the cell chi-squareds? We add them up. Can you add up all those numbers in your head and tell me what they are? Now, I'm asking you to cheat, but you should know if you add up all those numbers, if you add up this plus this plus this plus this, someone's doing it, but you'd say, Brian, the answer is this. What would we have right there? What is the answer? So what is the answer? If you add up all those cell chi-squareds, what would you get? The sum of the cell chi-squareds, great job, Sammy, right there, is the Pearson chi-squared test statistic right here. The sum of the cell chi-squareds is the Pearson chi-squared test statistic. This plus this plus this plus this blah, 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 is that value right there. That's why we use it. That's how we calculate it. And Leo was doing something super awesome. And we'll just mention degrees of freedom. The Pearson is telling us the answer. Go to my Pearson, find your answers. I mean, not literally, but Leo looked at this immediately and told me the degrees of freedom. Now, we're going to do this the easy way and the hard way where mistakes can happen. Okay, so the number one way to figure out degrees of freedom for the chi-squared test of independence is to look at me and say, Brian, that's a what by what. So fill in this full sentence. I used to do this in class. Brian, that's a blank by blank. So start by doing this. I want you to start by doing this. Say, Brian, that's a blank by blank. Look at the matrix right here. If you're wondering what I'm saying, great job. Leo's got it in the chat right there. Oh, we've already got it picture taken. Brian, that's exactly like there. Brian, that's a 2 by 5. Why are we saying 2 by 5? Because we have 1, 2 right there, and then 1, 2, 3, 4, 5. So that is a 2 by 5. Brian, that's a 2 by 5. Now that you've said 2 by 5 and Samuel's showing the formula, you're just going to drop each one by one. There's your equation. Write the equation right now in the chat to find it. So just practice right now and see if you know the equation I'm holding up. Remember we said, Brian, that's a 2 by 5. Samuel's got the equation in the chat. Try and fill it out. 4 by 1. So how many degrees of freedom are there? 4 times 1. 4 degrees of freedom. All you do is just drop the rows by 1 and the columns by 1. Now be careful. You'll see the trick right here. Look at this. Be careful. Brian, that's a what by what. This is where mistakes happen. This is the harder way of looking at it. you'll see, be careful. Brian, that's a what by what. And think, Leo's already shown us some tips right here. Read what Leo's saying, and then let's see. Let's see what he'll say in the chat, because Leo's showing some tips right there. Rock knows about those totals.
It doesn't matter.
This is the exact same data, right? This is the exact same data. We haven't changed anything about this. It's still a 2 by 5 or 5 by 2, whichever way you describe it. It's still the same. It's the same data. This is the same problem. The problem is a lot of times people use the total columns here, but those aren't answers to the questions. Those are just the marginal displays. So it's still a 2, whichever way you want to say it. There's 2 right there. And then there's 1, 2, 3, 4, 5. And so it's a 2 by 5. Another way to find the degrees of freedom is actually to go in here and to do this. If you do this, look what you're left with. 4 cells. So that's another way just to visually see it, but don't use the totals. You could also do that on the mosaic plot. Just cross out. If you go here to the mosaic plot and you cross off one row and column, you can see it because you're literally visually deleting it by going here and saying, we'll go black pen and go, that's a red pen. If you delete this and you delete this right here, you'd be left with these 4 cells right in here. And there's the 4 degrees of freedom. The 1, 2, 3, 4. Just an alternative solve right there. Be careful. It doesn't look so pretty there. It looks more pretty down here. But remember, there were 2 rows, 5 columns, delete 1 row, delete 1 column, multiply them together. But yeah, we'll do 1 more degrees of freedom. I love these questions because I want them to be quick and simple, and that you can just solve them instantaneously. Let's look at someone's relationship status, distance from campus. Brian, this is a what by what. Be very careful. This is a trickier one. Brian, that's a what by what. And then tell me the degrees of freedom. Be very careful. This is a trickier one. Be very careful. I think I've got it. I have to leave. Yeah, awesome. And this is all recorded, Majed. Congratulations, Majed. Great work. Yeah, exactly. And then check out the video afterwards. We'll put in the timestamps. We're going to do confidence roles interpretations next here. So, Brian, this is a what by what. And then what are the degrees of freedom? I'm going to disappear so you can see the full thing. So, Brian, that's a what by what. Be very careful. It's kind of overflowing off the screen. But that's a what by what. You're welcome, Majed. It's a 5 by, that is correct, Alexa. Brian, that's a 5 by 5 right there. That's a 5 by 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's hard to see. That is, you can see it right there. 1, 2, 3, 4, 5. That is a group right there. That little tiny group. There we go. Samuel, you got it. 5 by 5. Drop by 1. Multiply 16. It's 4 times 4. So 16 degrees of freedom. You just figured it out right there. Great work. Let's say, can you solve? So we're just reviewing one more time on this, and we're going to do confidence rolls. Ooh, it's going to be too large off the screen, isn't it? Oh, no. Yeah, it's too big off the screen. Degrees of freedom real quick. We're just reviewing. Degrees of freedom here. And this is going to have a high p-value because it's very similar across. Degrees of freedom here, this is a what by what. What are the degrees of freedom? This is where you just like get really good and quick at it. I can't use the dating thing because it's too long. 4 degrees of freedom. Brian, that's a 2. 1, 2 by 5. 1, 2, 3, 4, 5. 2 by 5. Drop by 1. 1 times 4. Let me not use the dating one again. I need to use distance from campus. Let's use Greek life and born in TN. Okay. Here we go. So we're seeing degrees of freedom here. I know I'm just doing degrees of freedom endlessly, but we can do them like this. Degrees of freedom here. 1. Brian, that's a 2 by 2. 1 times 1. 1 degree of freedom. Seen right there in the output. Okay. So let's do an expected count. How many people born in Tennessee would you expect to be in Greek life? How many people born in Tennessee would you expect to be in Greek life? How many people born in Tennessee? See if you can solve this from what we were practicing a moment ago. Formulas are not on the screen, so we do some more difficult solves. But if you have your formulas written down, how many people born in Tennessee would you expect to be in Greek life? How many people born in Tennessee would you expect to be in Greek life? And then we can check our answer here in a moment. See if you can get it. So if you don't see it, once we solve it, rewind the video and try to solve it for yourself. Number one way to practice. So we're trying to find the expected value. The expected value is going to be the row total times the column total over the grand total. And I think Samuel might have an answer right there, 174. That's probably right, Samuel. Let's check that out. Sounds rightish. So what Samuel did is they went, people born in Tennessee expected to be in Greek life. So born in Tennessee would be this group right here. In Greek life would be this group right here. We take those two numbers, multiply together, and we divide by the grand total. So does that make sense right there? And great work, everyone, practicing. That's how we find the expected. We take the row total for it times the column total for it, so we zero in on it. Notice how whenever you're doing this, you're taking the two values right here and just kind of crossing in where they connect. Then you're going to take multiply and divide by the grand total. And we go 487 times 288. And we want all these to be greater than what number again, chat? Every one of these needs to be greater. I just did a math error, didn't I? We want all of these to be greater than... See, I tell you to do it with me because then I can see if I made a math error. And easily visualize. Exactly. Do the crosshair to be like, there's the one we're doing right there. Like crosshair in on it and then divide by the grand total. So that is the row total times the column total. That's the row total times the column total over the grand total. Like zero in on it. Like, you know, go row total of it, column total of it, and then divide by grand total. So that is 147. Now we can check that answer very quickly by going here to expecteds, and we can see it is 174, excuse me. Now let's find the cell chi-squared. And the cell chi-squared for this one is going to be what? The cell chi-squared is going to be about 0.6. It's going to be about 0.6, I think. Let me think. No, it's going to be 0.57, I think, about. Who has it? I say 0.57 is my guess. How close was I? Find the cell chi-squared for this. So, oh, it's 4? Dang, I was a little bit off there. More like. So we're asking the cell... I usually put that down there. Chi-squared of the cell. So the chi-squared of the cell, great, I was wrong. I should have just said 0.5. That would have been close enough. Is the observed minus expected squared over expected. So we take the difference between these two numbers right here, because that's the observed. Do you remember the count is the observed? I think it's a common error. So the count is the observed, and then the expected is literally the expected. Like that value is that value is... Trying to do a little color coding here on the... So those are the values right there. Observed minus expected squared over expected, and you do get those formulas. So plugging in the numbers right here, we observe a value of 165. We subtract 174.015. We square that, and that's about 91 or 81. Oh my gosh. And divide by 174.015. And there it is right there. Good work. That is the cell chi-squared. And once again, to hammer home our knowledge, if you take all these cell chi-squareds and add them up, what would they add up to? Quick, first person, 1,000 points in the chat. If you can add up 0.396, 0.7130, 0.2597, 0.4767. I'm doing it in my head. I think it's about 1.83. And what's that next digit? Alexa's got it right there. We all didn't do it in our heads. It is right there. It's the chi-squared test statistic is the sum of all the cell chi-squareds. Once again, repeating our knowledge. And what we would do, I'll mention this last part, this is not test relevant, but it's decent to know, is if we had this chi-squared test statistic, 1.836, we'd go over here to the chi-squared applet. So this is why we get the chi-squared test statistic, to go over here with that where's the chi-squared? 1.836, degrees of freedom 1, and there's your p-value right here. So this is what you would do if you didn't have JMP doing the work for you. And the applet's going to get you, if you notice, it is this p-value. It's just there probably have more decimals that we don't see. So you would go to the applet, enter in the degrees of freedom, which tell you the shape of the chi-squared. The degrees of freedom control the shapes of the distribution. And so you'd put in the proper degrees of freedom, 1, and then you'd put in the chi-squared, and you'd get the p-value, which Jump is displaying for you here, probably doing a little more calculations on the chi-squared than we can see in the background. And that is testing. That was a huge review of testing. I wish I'd put more timestamps in the video, but now we're going to do confidence intervals probably a little bit quicker, so stay tuned for confidence interval interpretations. I should have broken up each one of those into its own segment. I'll go back and do that here in a little bit. But how's everyone doing? We're going to do some confidence intervals. Say hey in the chat. Good to see you here, Sarah. So we're going to do confidence intervals next. And maybe I should have just put like... Here we go. Because we went over an hour on that segment. I like segmenting the videos, and I'm like, oh, that was an hour. Okay. Interpreting confidence intervals. Let's go with 1 proportion. Okay. Got my peach Red Bull though. Oh my gosh, dude, you have to try coconut Red Bull, coconut berry Red Bull. That's the best, Leo. That's my personal opinion. Okay, let's do some confidence intervals. Here we go to the main screen. Okay, so once again with confidence intervals, we're starting off with the first confidence intervals we did. So when we do confidence intervals, we actually get one right over here. Oh, I thought we did. We don't have one yet. Okay, so there's our confidence interval right over here. Let's go grab it. And that's kind of cool. More on that in a moment. Let's grab... Yeah, we just want that one output on there. I don't want to bring too many topics yet. I want to focus. Okay. There's our first confidence interval. Now, when we do proportion... Oh, Leo. Leo, no. It is still pretty good, though. Oh, that's... Kenneth, that's some S-tier Red Bull right there. Coconut berry slushy Red Bull. So wait, let me put this in the chat. Coconut berry slushy Red Bull. Frozen Red Bull greater than anything Leo says. It would probably if you did it too much. You have to get that right. It's like when you get Coke in the freezer and you get it to just right the amount. Just right. You have to do it. It's tough. Gotta be careful. Don't want it to explode. Here we go. Time to get serious. Retime stamping. Here we go. Okay. We have a confidence interval right here, and we're talking about the proportion of people who've broken a bone. So what do we make confidence intervals from? First question is, what do we make confidence intervals from? Who knows the answer to that? A confidence interval is made from a what of data? A confidence interval... Leo, that's a quote of the day from... You got it. Quote 216, Leo. You're in there. Confidence intervals are made from samples. They're estimates of the truth. Confidence intervals are made from samples. They're estimates of the truth. Does that make sense? We went out and spoke to how many students in this example? How many students did we just use the data on the screen to tell me how many students were spoken to? And we asked him, broken bone. Have you broken a bone? How many students were spoken to? We talked to 806 grade up John and Samuel and Kai and Alexa and Leo. We talked to 806 students and we asked them, have you broken a bone? So we want to figure out the what of students who have broken a bone. Great job, Leo. There are 375 of them reported they have broken a bone, and 431 have said they have not broken a bone. So we want to figure out the what of students who have broken a bone. Now, just try to say, when you say it, ask yourself, does it make sense? Everything we say, and great job, Kai, right there. We want to figure out the true proportion. Also, you could think of it as the what. Ukai, you are 100% right. We would say in stats true proportion. And then what might people not in stats would say? I want to know the true what or the real blank of this. I want to know what is the real, another P word right there, which is the same thing as proportions. They might say, I want to know the true, like for all set to one students, what's the true, they might say percent. Well, you could do real number, but we probably want the true proportion of the true percentage, right? Like what is the true percentage of people? Because if you look, that's what we're trying to estimate right here is we have an estimate of the truth. And then we have a lower bound and we have up to an upper bound. Now, interestingly enough, that estimate goes right here at the center of the interval. So that estimate right there is actually between the lower boundary and the upper boundary. And we can do two different estimates. We can do an estimate of the proportion of people who have not broken the bone and the proportion of people who have broken the bone. I am 95% confident that the true proportion of people who have broken their bone is contained in the interval. Leo, that's exactly it. Leo, another 1,000 points. Keep the points rolling in. Leo, that would get all the points on the interpretation. So Leo has brought us to our interpretation right here. We're trying to figure out the truth from this sample. And so let's do our interpretation. I am blank percent confident that the... What do you think is the hard part? Leave it at that. Let me say true. It's contained in the interval blank to blank. So the hard part for people on this is always the contextual part. Exactly. The contextual part is the hard part because the easier parts of this are going to just be, I am this percent confident. So I am, and let's do a new color right here. I am, and if we want to talk about the people who've broken a bone, we just insert the percent confident right there. I am 95% confident. So put that right there. That the, and now we need the context of it, and that is the hard part. We'll put it in like some orange right here, like a warning orange. And why did you say proportion, Leo? A lot of people get confused on this. Why did you pick true proportion of people who have broken a bone? Why did you go with proportion? This all actually boils down to the start of the class where it really goes down to Alexa wrote, yes, great job, Alexa, right there. Great job. Because we're working with categorical data. This is categorical. And so since it's categorical, we're dealing with the true proportion. So that indicates to us we're dealing with proportions with categories. So that's proportion. So because we're talking about categories, the proportion of people who are in this category, great job, Alexa and Leo right there. I am 95% confident the true proportion of people who have broken a bone is contained in the interval. And from that point, it's just lower to upper. I mean, I'm trying to think what else I can say about this output, but hopefully it's making sense on what we're doing right here. I'm going to disappear again so you can see it, but that is what we have right here, and this is what this output is showing you. I guess another thing we could mention is what is value 1 right here, and I'm speaking specifically about this value, and what is this value right here, value 2. What is value 1? So my question right now is what is value 1, like in notation, and they'll put a value 3 on there. And what is value 2 in notation? And then what is, we'll put a value 3 on here. Knowing the notation is always key for this stuff too. So what are those values in notation? So the top right of this, like, oh, good. Can't there. Can you pick the 90? Yeah, good job right there. Leo helping out, 100 points. Thank you, Leo. And that is the 1 minus alpha. Yep. Great job. No, Leo, 1,000 points. Keep it up. Keep answering. I looked down and you answered a question. We love that here. So Leo's awesome. And then it's you too, Kenneth. Also tells you alpha 2, by the way. Correct. We know alpha is equal to 0.05. Great job, Leo, observing that. This would be similar to an alpha of 0.05 on a two-tailed test. And because you can do 1 minus alpha to get the confidence level. These are the confidence levels right here for the intervals being created. So 1 is P and 2 is P hat. And so good job, Alexa, right there, 100 points. If we have, and you're right on, you got 2 out of 3. Values of P and P hat must be contained between what and what. So here's a good check, Alexa. Values of P and P hat must, or Q hat, P hat, P naught, P, all those things must be contained between what and what? All the values of P, P hat, P naught, Q, Q hat, Q naught, they can only go as high as 1, right? 0 and 1. Great job, Samuel. They can only be between 0 and 1. And Leo has done the last one right there. Great job, Leo. We have right here that the first value is equal... Well, we don't want to do that. The first value is x equals 375. The second value is n equals 806. Now, what could you derive from x and n? What could you derive from x and n? What could you find from x and n? P hat. So you can check right there, x over n is p hat. Just if you divide those numbers right here, you will get p hat. So those numbers divided are p hat. Yeah, Troy, good to see you here. Great work. Troy just doing a great job right there. We got all the... Oh, you guys are tied basically. Almost on points and hours. We should make a... Wait, we're doing this. We're in an in-between segment. We're about to go to the next segment. It is official, everyone here. We are making a new Stat Nation level right here in honor of this. Give me a second and check your points here in a little bit. How many more points do we need? I'm going to have to fix someone's points. All right. Name. All right. Give me a second, then we're going to start a new thing. As long as you both are cool with this. Okay. All right. There we go. It's in there. 2 seconds, then we're going to start the next thing. What? Oh, no. Don't worry. Kenneth, you're getting lots. Kenneth, let me throw you. Kenneth, I want you to check. You're about to get max extra credit, Kenneth. So, Kenneth, you're right there, max extra credit. And Troy is closer to a new thing than Troy's been. So, Kenneth, you're going to break the extra credit boundary right here. This pushes Kenneth over the boundary to get the 1.2. Don't worry, Samuel. We're all just here for fun and enjoying. And then Troy and Leo, you should check out your new bonus here. And shouts to everybody. Kaya getting tons of points right there. This is an honor. Troy and Leo just head-to-head competition. We'll see if Mewbot's updated. Then we're going to start the next section right here. So there we go. The Troy/Leo level right there in honor of your 300,000 points near tie. And Kaya, keep it up. I think we have a Kaya level, right? So that's the Troy/Leo level right there. And I think the first 2 people there to get it. Oh my gosh, you're 5 points short of the Troy/Leo level. Here, wait, let me hit the 5-point buzzer or the 10-point. Okay, there you go. We have a Kaya level. Now we have a Troy/Leo level right there. 5 points away. There you go. I threw 10 Mewbucks out there. Okay, so here, let's get the next section up and going. We're going to do confidence interval interpretations for one mean. Okay, so I'm getting the next section up and going as we talk right here. I have like, these are like the longest bookmarks I've put in. All right. So one mean, which is t-test, and let me grab the timestamp. 1:39. Probably try to go 2.5 hours today. Might do like Saturday or something. You never know. Okay. So right now we're going to talk about the one sample T right there. The one sample T. Great job, Kenneth, getting max extra credit. So right now we're going to talk about the one sample T interval. Now, with the one sample T interval, what do we need? What do we need for the one sample T interval? What do we need for the one sample T interval? What do we need for the one sample T interval? What do we need for the one sample T interval? Now, when we say Mr. T, we're talking about means. Kai knows right there. We're talking about the one sample T interval. The one sample T interval. So the one sample T interval is this right here because we're dealing with a quantitative variable right here. High school GPA, the interval to estimate it, is going to be a T interval. And look, it even says mean right there. Mr. T is mean. I'm sure he's a nice guy, but if you're doing drugs, he's pretty mean. He's not going to be happy with you. So let's go ahead and edit, copy, and bring this over here to the main screen. There we go. So when we do this, we are going to interpret this interval the same way we interpreted the previous ones. Now, we see the context of this right here, and that's usually where people lose points. So let's go here and interpret the context of this. Okay, I am blank percent confident that the true blank is contained in the interval blank to blank. Now, I did it again, but do realize that a lot of intervals are 95% confident. Do check the percent confidence level. I'll switch it up for the next one. I think I know how. So the easier parts of this are to find the boundaries of the interval. The harder part for this, where people usually get stuck, is finding the context of it. Now, I am blank percent confident. So we need to mention how confident we are. And you can use either one. It's just going to be 95 right here. I am 95% confident. You can say we are. It's fine either which way. Rock knows.
It doesn't matter.
And so we'll see what people say. And then what do we say there next? What is the context of this? I'll show you the lower and the upper of the interval. So the lower of the interval, that's the upper. The lower of the interval is going to be this. There's the lower value. And the upper value of the interval is going to be this. But the context is where people lose points. The context of it. That right there is where the points are lost, mostly. I am 95% confident the true mean high school GPA is contained in the interval. There you go. There it is right there. That's it. Alexa's got it. Good work right there. Alexa, excellent job. I am 95% confident the true mean high school GPA is contained in the interval blank to blank. That's all it is. And when we think about this, what are we doing? We're saying mean because it's quantitative. And then we just talk about the context of it. I am 95% confident the true mean of high school GPA is contained in the interval 3.78 to 3.83. Now be careful here. Who can tell me the margin of error of this? And I'll show you a magic trick. Not the kind the Joker does. What is the margin of error of the interval? Who can solve the margin of error? Take a moment right here. We've already interpreted it. Kai's got the answer in the chat. The margin of error. I'm putting it in the chat right now. It's about that. I'll show you a trick. Maybe it's a little bit bigger. Yeah, maybe that's my extra guess. How many decimal places was I accurate on it? Find out. Find me the margin of error. I'm doing it in my head. How am I doing that? And then I'll show you a trick and why. Well, rounded. I think so, right, Alexa? Rounded, it's going to be that. Give me more decimals. It's got to be a little bit smaller than that. Got to be a little bit smaller than that. Good answers, Alexa, though. Good answers. A little more decimals. So was I right to the next decimal, Leo? I want you to find it exactly, because I estimated it really quickly. And I'll show you what I did, which might not apply to everything. So if you want to find the margin of error would be found the following way. The margin of error is always known as what the length of the interval. The margin of error... well... oh, Lex has got it. Half the length of the interval. Half the length of the interval. You're always free to share or not share, whatever you want. And or you can find each other on the Discord and message there. There you go. Guys are cracking me up in the chat. Oh, I love it. I will say this. I am so glad. I have had people literally start clubs and meet each other because of our online classes. So I've had people make friends and like I've had two groups of people get married from my classes. And I've had one group of people start a club. Like, these are the things I know about. Like, they have said, hey, Brian, we met because of you and we're getting married. And I'm just like, you know, so the center of the interval, we're going to write these in here as estimates, is 3.8088. Okay, there we go right there. And then the upper bound of the interval is 3.8358. And then the lower of the interval is 3.7819. And then what do I find right here? Oh, man, Kenneth, that sounds good. Do beef jerky. Ooh. What's the best flavor, Kenneth? You got to tell us the best flavor now. Like a spicy flavor or a teriyaki or something, or like there's some flavor, right? You got to tell us the best flavor, Kenneth. Or shout out your dad's, if your dad has a store or somewhere to go. There's a place in Kingsport that has really good jerky. But dude, I can just plow through a bag. That's awesome, Kaya. My last name stayed the same. Crockett Creek, look it up if you're in Knoxville. So check out Blazing Cajun or Teriyaki's always a good bet. Shout outs to Crockett Creek right there. Next time I'm in Knoxville, I'll swing by Kenneth. I'll pick up maybe 2-3 bags. Especially if they got something like buy 3 bags, get a 4th free, or buy 4, get a 5. I'm sorry, I know I'm gonna eat it. I'll buy 5 bags of jerky. I'm just saying, that might last me the weekend or something. Sweet and hot, yeah. Oh man. Get a little bit of like peppercorn on it or something. Woo! Anyways, you guys got me thinking about jerky all the time right here. It's good stuff. Good Tennessee. I don't like deer meat though. Anyways, okay. What do we need to find from this info? Brian's going to focus. What do we need to find from this information right here? What do we need to find from it? Remember, we're trying to find the margin of error, right? Margin of error seems more complicated when there's a bunch of decimals, but you can do the margin of error in your head. So margin of error is pretty easy to calculate. If I tell you, I will arrive to your house, we're friends. I'm going to arrive to your house sometime between 5 and 4 p.m. I'm going to arrive between 4 and 5 p.m. Well, what is Brian's estimate for when he'll arrive? I'm going to arrive between 5 p.m. and 4 p.m. We're going to play Smash Bros. So I'm going to arrive between 4 p.m. and 5 p.m. What is my estimate for when I'll arrive? My estimate for when I'll arrive is what? My estimate for when I'll arrive is what? And this, we're just seeing how to find the margin of error and what it is. It's a little bit of uncertainty. 4:30, and probably about 4:30. Like if you say, well, when do you think you'll arrive? I don't know, around 4:30, between 4 and 5, right? So 4:30 is your estimate right here, and that's called the center of the interval. The center of the interval is just the what of the two numbers. You can do it mathematically right here as upper plus lower, and it's just the what of the two numbers. The center of the interval is just the what of the two numbers, which we just kind of did in our head. The center of the interval is just the what of the two numbers. The center of it is just the what of the two numbers. Because if you do upper plus lower divided by 2, because 4 plus 5 divided by 2 is 9 divided by 2, which is 4.5. So it's just the center, the average of the interval. It's the mean. It's the center of the interval. It's the estimate. So we can see how that is found right here. But now we don't want to find the center of it. We want to find the length of the margin of error. So the margin of error is just, in words, what the length of the interval. So look at the margin of error and just be like, oh, here's the length of the interval. The margin of errors are just what the lengths of the interval. As best I can draw, it's just half. This is a 1 hour interval. 1 hour. Half of it is a half an hour. So we overly complicate things sometimes with decimals. So all we need to do right here is think of a formula. The formula we want is upper minus lower divided by 2. And try plugging in those numbers. You can plug in the numbers we have on the screen right here, which is going to be 5 minus 4 divided by 2. Well, 5 minus 4 divided by 2 is half an hour. So that's 0.5, and we're talking about an hour, so half an hour. Well, with the top interval, it's just more complicated math. We're just going to go the upper value, which is 3.8358, minus the lower, 3.7819 divided by 2, and there it is right there. But if you want to know something interesting, I didn't do it that way. I didn't solve this one that way. Here's what I did. I didn't use the formula you see up top. What I did is I used the following formula. What is the only value you see in this interval right here that here's the margin of error. So there's the margin of error. What is the only value you see on the screen that's currently in that formula? So I'm showing you how I found it. This is an advanced thing, but it goes to reading the output. We do see y bar. Leo, you are correct. Y bar is the sample mean, and that is up there, and that's the estimate. But that's not part of the margin of error, which is going to be the plus or minus. So Leo, that is correct. Y bar is the estimate, and y bar is right there. That's y bar. Great job, Leo. There's one other quantity, though. The other quantity that is on here standard error. If we make a standard deviation, so standard deviation is on, standard deviation is on there. And actually, so you could find the standard error. So the standard error is on there, and the standard deviation, which is S, and the sample size there, and the standard error is the full quantity. So then the question becomes, what is the t statistic, right? The t statistic at this point is basically the z. And the z for a 95% confidence interval is basically what? The z for a 95% confidence interval. Now, this is an advanced quick solve. It's how we do things in 320 to be like, well, it's usually about this. 68, 95, 1.96, right? So it's basically 2-ish. So watch what happens. Remember that number we just found right here. There's the number I'm putting in the chat. And remember, z's and t's are different, but with high degrees of freedom, the t's and z's are very similar. So if we take this standard error and times it by 1.96, this is not how you would solve it, but it's how you would estimate it. This is a little bit of using stat theory to solve it. And there's the number we get. And I'll put that in the chat. And it's actually down to the fifth decimal. T's matter more. And this is the last thing I'll say on this. T's matter a lot more when the degrees of freedom are water. T's matter a lot more when the degrees of freedom are water. T's matter a lot more when the degrees of freedom are water. This is where you see more divergent value, when they have low degrees of freedom. Low degrees of freedom, the T looks very different from the Z. But watch as we go to 805, it even says to use 1.96 right here. It's just that the decimals are down to the second decimal accurate. What's funny is I love it at 60. It's actually 2. So if you have 120, it's 1.98. The T and the Z converge. And at high levels of degrees of freedom, the T and the Z are virtually identical. And one of the great things about using statistical software is you don't have to calculate the T. If I want to make, just a very quick aside on this, if I want to make a 95% confidence interval, all I would do right here is go to t.test and run some data. And there's my 95% confidence interval. That's it. Done. I'm 95% confident the true miles per hour that these cars will get is contained in the interval 17.917 to 22.26. That's it right there. And I don't have to do anything. I think the argument here is level. No, I don't know what it is to change the percent confidence. But I could change the variable and all that different stuff. And I do it different ways, different times. But anyways, it's important to understand that statistical software is going to find this for you and to understand what the margin of error is and how to find it. There's the upper... Here's the lower, or here's the center, and there's the margin of error of this interval. But we're not using R, so I'm not going to focus on this so much, but the concepts remain the same. Great job right there. Jump, PZ translation, standard error equals standard error, the mean, standard error of Y hat, Y bar, Y bar, Y bar, standard error, Y bar. Great work right there, Terry. Awesome stuff right there. Okay, so now we've got our next. We're doing a little above and beyond today. Standard errors. Now we've done one mean, so what should we do next? Does anyone know? We've done one mean, so what should we do next? We've done one mean, so what should we do next? We've done a confidence interval for one mean, so what should we do next? We have now talked about one mean. Let's make a confidence interval to estimate the difference between two means. Kristen, great to see you here. Now we're going to take two samples right here. What does the two sample mean? The 2 sample t means the x variable will be what? The 2 sample t means the x variable will be what? The 2 sample t means the x variable will be what? The 2 sample t means the x variable, because we need 2 means categorical. So we see an x variable that's categorical like your honors program, and then we see a y variable that is quantitative like your GPA. So let's see, and think about the null hypothesis right here. The null hypothesis would be, and we're not doing a hypothesis test, but we can talk about it, is that there's no difference between the high school GPA of students who are honors students and not honors students. Now, we like to do a little high-level questions, medium-level, and easy questions. So if you think about p-values for this, for there being a difference, do you think the p-values will be high or low if I run this as a test? And we'll run it here in a moment as a test. Do you think the p-values here will be high or low to test to see if there is a difference between the high school GPA? So we're going to see if there is a difference, the alternative. Well, careful. Do you think there is a difference? Do you think there's a difference between the high school GPA of honors students and non-honors students? Yes or no? Do you think there's a difference? So we're going to look at the GPAs of high school honors students and non-honors students. So Alexa, great work, Alexa, right there. Yes, I think there is a difference. And the null hypothesis is that there is no difference. So it sounds to me like we're going to reject the null. It sounds like when we run the t-test, that the p-value will be low. Does that make sense how we kind of theorized? We had an idea that there was a difference. And can anyone tell me what that difference was that you saw? What difference did you observe between the honors and the non-honors students? What difference did you observe between the I saw a difference of this between the groups. I saw a difference of this between the groups. What difference did you see? I saw a difference of this. I saw a GPA difference of 0.311. That's the difference right there. We do love to review our output whenever we see output. How in the world are they getting that T statistic right here? Love to review our output. What's that? How are you getting that? So the test, we're going to do the enroll here in a second, but the test is going to be y bar 1 minus y bar 2 over standard error, which we can just write standard error diff. So how are they getting that? How are they getting that T statistic right here? That is a T with degrees of freedom that are too complicated to do by hand, at least for us, me included. Great work right there. Alexa has pointed out that the difference standardized is the T ratio. So the standard error of the difference, which is S sub 1 squared over N1 over plus S sub 2 squared over N sub 2. My gosh. Difference divided by standard error. Exactly. We're just standardizing that difference to get a test statistic. Now, here's something I really wanted to point out. The reason I'm mentioning this is that T right there, that T you see right there is not. It's not the same. It is not this T. Why do we often put a star on that T? These two T's are not the same. I guess technically they could be in rare instances, but they're not designed to be the same. Someone says, well, what if you wanted to make a... No, okay, well, you could find a way, but generally not. I'll write the standard error out this time. The standard error is S sub 1 squared over... 1 is chosen, 1 is given, exactly. Well, one is solved for mathematically, 1 is given related to % confidence. Which one of those is solved for mathematically, the test or the interval? Which one of those is solved for mathematically? And look at the way it is up there. Which one of those is solved for mathematically? Oh, Terry, I like that. It's critical you know about this. It's critical because that's the critical value for the interval. This is the standard error I was speaking of. That is the same in this formula. And that's the same in this formula. The top one is solved for mathematically. The star, which is super duper important, the star, we'll do this in a different color right here, means it's relative to this % confident. The star means you're picking your T such that you cover 95% of possible values. So the T right there is super important. I'm going to highlight in green, I guess, but it's not the same value, because I don't want to do that, because we're going to highlight this in green right here, kind of connecting the output. So that right there is that T, but the lower T, I don't want people to think it's the same. It's not the same. I'm too afraid to shade it in a different, we'll color it a blue. It's a little hard to see. Let's go pink. They're not the same. And the T value, correct. Now be careful. The T values for what's would be given to you. Because someone might say, well, you made us solve for a T value. And technically we could have you solve for these, but generally you give them. And you can't, the T values for what's would be generally given to you. Generally given to you. There could be a math problem that has you solve it, but you wouldn't be calculus deriving it. It could be like, I'm not a big fan of those types of questions. I don't think we have any. The T for the what would generally be given to you, because these are different T's. The T for the what, which is the theme of this section we're talking about, the interval, that's the confidence interval. So this is the T test, two sample T test, two sample. It's still a T test, two sample T test, and this is the two sample T interval. So that's the two sample T interval. If you need a critical value, we'll give you exactly as Terry said right there. We'll give you critical values. So the T for the interval is decided on the percent confidence level. And so when I go to the applet, I will be asking it for a T with what? I'm trying to make it so you can see it. When I go to the applet, I will be asking it for a T with what? Because there's infinite T's. When I go to the applet, if I was doing this, like for what we have to do for you, I will go to the applet here, just so you can see, and I will go and ask for a T with what? 90, great job, Leo, right there, 95% confidence. And then I also have to tell it, because we need to know what T we are using. So I'm going to say I want 95% confidence. So I use this one right here. It says p-value, but we're just going to go with it. And then Alexa's already put in the degrees of freedom, 128.3 degrees of freedom, and the T statistic is 1.979. So, and it's going to be basically the same. And Jump does this all for us, finding the T we are using. And remember, once again, we talked about a moment ago that as degrees of freedom get higher, the T statistic approaches the Z statistic right here. So if degrees of freedom are smaller, the T is going to be more deviating away from what the Z is. This isn't to say, Rock,
It doesn't matter.
It does matter. And that's why modern statistical software always uses the T to do these calculations, even if the differences are very, very tiny. So you do need to know that the T is a more exact calculation created by who? Who is our friend working at the beer factory? Maybe he was eating some jerky and enjoying his time. I got to load it back in. I'll load it between segments right here. I'll load it back in. I lost it because I reset the computer. We got things working for yesterday. William Gossett, William G right there. Funny story, Ronald Fisher, who actually you did see a Fisher test on here for half second. There's Ronald Fisher. He created this test. Ronald Fisher did not like William Gossett and would not publish his work, so the name student was a pseudonym that William Gossett worked. I imagine they're like, oh, that beer guy, we don't want to publish that beer guy's work. So he's like, oh, but would you publish students' work? And they're like, ooh, that's some really good statistics. And they published it, and he's like, ha, I got into your journals. So pretty interesting story about how William Gossett, working at the Guinness Beer Factory, couldn't get his work published and called his distribution the student T distribution. So this is students, as in students is the person, and then T is just Gossett. Maybe it chose Gossett's T, you know. It is William Gossett, though, who worked at Guinness Beer. And fun stuff. Yeah, no, don't. Yeah, we're not doing the spelling. Why it said students. Just pseudonym, fake name right there. Really, I like showing it when I have it. But Guinness, Gossett, Guinness Beer. He actually has a plaque at the Guinness factory So make sure, yeah, I think this is fine right here. So Gossett's plaque right there, and then people love putting pictures of. It's just a cool stat story to be like, oh, that dude, like the beer guy made the thing, and so how did beer change statistics for forever? There he is. Yep, cool story and stats. And look at that. They got a T distribution. It's for all intents and purposes is basically the normal. It's a more finely calculated normal. Accounting for smaller sample sizes where we might not have estimated the true standard deviation of a distribution, allowing for greater variation in the tails of the distribution. The beer guy made the thing. You bet it. He did. So let's go to our interpretation of this interval now that we understand the differences between these t's and how are we going to interpret this interval. Okay, so we need to grab our interpretation right here. I am blank % confident that the true blank is contained in the interval blank to blank. This one's a tougher one. Who's got me on the interpretation right here? This is a tougher one. Take a moment, see if you can do it. I am blank % confident that the true blank is contained in the interval blank to blank. We'll see what people say. Remember, this is your chance to try writing it down. If you're watching this in future, you can fast forward. But the number one thing to do is to try to write it down. Make sure you know what you're interpreting. You're seeing a two-sample t-test, so you're comparing the two means. What's the context? Oh, we're comparing GPAs of honor students, non-honor students. So thank you, Leo, for that question right there. What's the context? This is GPA, is the Y variable of interest. And then the X variable right here is honors. Good question. What's the context? Number one thing. So the context is the difference between the true mean of people who are in the honors program and the true mean of people who are not. You can always put muse up here, the true mean difference, because remember we're doing the difference. There's the difference right there. I'm using that color for something else. So the difference right here is what we're thinking about. We're trying to understand the true difference. Now that's our estimate of the true difference. That's the difference between the sample means. We're trying to understand the true difference between yes minus no. Our best guess is the sample difference. We want to estimate the true difference. Careful, Zach. 100 points, Zach. Now, since it's Mr. T, we won't say proportions. Since it's Mr. T, we won't say proportions. Since it's Mr. T, we won't say proportions. Because we're doing quantitative here. So anytime we talk about the T, Mr. T is mean if you're doing drugs. So if anyone ever wonders why I say that, I would never want to say anything mean about Mr. T. He seems super awesome. And so he's only mean if you're doing drugs. We're doing means. So this won't be proportions. It's a quantitative Y, and the Y variable indicates that we're doing means. And so since we're doing means, we need to say something like that. So take a moment. We haven't gotten a full answer yet, but give it a shot. We haven't gotten, and it won't be percentages. So let's take a look. Let's see what we got. Take a moment. No one's giving a full answer yet. We got this. See if you've written down. I am 95% confident the true mean difference between GPs of honors and non-honors students is contained in the interval. Boom, right there. And you might say, Kristen, right there. Excellent work. 1,000 points. We've been going crazy on points today. We even got a new Troy and Leo level. Kristen right there, I think, has it full. I am 95% confident that the true mean of, and then the true mean difference between. So make sure right there, Leo, does that make sense? The true difference between the mean GPA of honor students and non-honor students is contained in the interval. And then you could say with honor students looking to have higher GPAs. And why does it look to you that honors students probably have higher GPAs than non-honors? Don't just go with, oh, they're honors students. But when you look at this interval, that's the positive side of it. That's the negative side. And what do you notice about this interval? What do you notice about this interval? I am 95% confident the true mean difference between GPA of honor students in the honors college and students not in the honors college is contained in the interval bank to bank right there. And then probably add in with evidence honors students have higher GPAs. And the whole interval is positive. Does that make sense? The whole interval is positive. What value is not contained in this interval? What value is not contained in that 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 interval? Someone's probably putting in the chat as I finish writing this right here. 0. So what are you going to do to the null hypothesis? So if you were to do this test right here, the does not equals test, which can be related to the interval, what are you going to do to the null hypothesis that there is no difference? So if your null is that there is no difference, you can reject it because 0 is not in there. You're saying, no, I have evidence. So we just went back to testing again. We did the test via the interval. So you were able to reject this null, and you rejected this null at the what alpha level. We're just connecting this output right here. You rejected the null at the what alpha level using your confidence interval. You could say, now we did test interpretation a moment ago, but if you have the idea of connecting them, you could take and your confidence interval 1 minus confidence level is equal to alpha right there, or 1 minus alpha is equal to confidence level. They are complements of each other. So alpha plus confidence level is the 100% of the curve shade if we use analogous tests and intervals. So you would say I can easily reject it because 0 is not contained in the interval. But once again, do realize if you're doing the p-value stuff, go back to where we interpreted the results using the 2-sample t-test results. Okay. We've done a lot of review. That is the 2-sample t output and how to interpret it. Let's do one more section of this video today and talk about degrees of freedom. It's a good thing to do. And then we could take a few more questions. We've been going for 2 hours and 12 minutes. Let's do a degrees of freedom talk. How's everyone doing? I know I ask that every time right here, but Alexa, Leo, John, good to see you. John joining in. How's everyone doing? We're going to do talk on degrees of freedom next. Degrees of freedom. Finding and using. Okay. Still tired? Yeah, I feel it, man. I'm slowly waking up. I try to get 8 hours of sleep each night. Like, I go to bed at like 1, 2, and I wake up at like 6, 7. I'm like, dang it. Gotta stop sleeping for 5, 6 hours. I'll sleep. Eventually. Clean people thought it was okay to vacuum at 9, 8. Yeah, I know, right? Getting sleep in because no more. That's awesome, Kristen. 100 points, Kristen. Good to hear that right there. Get some good sleep, get some good food, get some good exercise. Your mind, body, everything is all connected. So make sure to eat well, sleep well, drink well, all that good stuff. Drink some water, drink some healthy stuff. Have some fun, socialize with friends. Life advice with Brian here on Stat 201. Okay, let's talk about some degrees of freedom here. Taking the timestamp down. I say those things to remind myself. Let's head back to the main screen. Oh, no vacuuming. So here we go. We have 3 times that we used the degrees of freedom. So who knows what are the 3 times we talk about the degrees of freedom right here? Can anyone tell me? I might do a part 2 tomorrow even. Just kind of doing it. I've got energy. So I'm like, let's do it. Let's do it. So we are going to review on Sunday. That's already scheduled. I was like, hey, we got time today. Let's do some review today. When have we used degrees of freedom? When have we used the t-test, the 2-sample t-test? You got it. And then there's the last time, which we just did. So we have the t-test, and that's a quantitative y. We have the 2-sample t-test. We were just talking about that. 2-sample t-test. So that's a categorical x 2-level and a quantitative y. Notice how t-tests always have quantitative y's. And last but not least, the chi-squared. So the chi-squared test. Now, I do want to say this super briefly, chi-squared test of independence. There are other times to use degrees of freedom, which we definitely have not gotten into in our class. There's something called the F distribution, which is the ratio of 2 chi-squareds, and it has the numerator and denominator degrees of freedom. So we haven't even gotten into something like the F test and the F statistic, but that is used. So there's more instances of this. Why degrees of freedom? So we haven't even done the F statistic, but why degrees of freedom? What do you notice about me changing the degrees of freedom here? Why degrees of freedom? The question right now is just why. Why? Why do these matter? Why do these degrees of freedom here matter? And we're seeing it visually. the shape of the distribution. So we haven't even done this, but we always know the degrees of freedom control the shape of the distribution. So let's go to one we do know, the t distribution. The t distribution was the first time we did the degrees of freedom. And once again, the degrees of freedom here determine the shape of the distribution. We like to tell Mr. T coming in saying, I'll pay the fool, and smashing down the distribution. But then he gives it freedom to be normal. It's not exactly what degrees of freedom are, but it's a fun way to remember it. So the degrees of freedom, the more you have, the more normal the curve is. The less you have for the t, and this is the way it works for the t, the less normal the curve is. We were talking about this earlier, that as you have more degrees of freedom, it approaches 1.96 for a 95% confidence interval. So the t distribution right here is like the normal, but it's more narrow in the center with fatter tails. Great notes right there. The t distribution is like the normal, but more narrow with fatter tails. But for higher levels of degrees of freedom, it basically is the normal. You can see here the classic 1.96. So the population size is not the only thing that changes the p-value. The population size would have nothing to do with the p-value. Sample size, you might want to find me that exact question, Leo. I think there's something. Population size will not change p-value. Population size is not used in formulas. Double check, because it might be a different Canvas content. I don't remember that one off the top of my head. Take a look at it and I'll address that one. None of our formulas use population size. They use sample sizes right here of n. So population size would not be used in a formula. Anything about population, we could ask things like we're trying to estimate population stuff, but population size will not be used in formulas. But when we do degrees of freedom, what's super important is going to be how do we find the degrees of freedom? What is the degrees of freedom? Because that's going to say what is the shape of the distribution we are using to find these p-values, to find these critical values. So we need to know how to find this. And the one sample t, which is just the t-test. So this is also known as one sample t. What is, and Alexa just perfectly saying it right there, the one sample t is just n minus 1. So if I were to go over here to jump, and Alexa just crushing it right there. Great answers. Keep it up, Alexa. So if I go over here to jump and I say I have 806 sample size, it does use capital N. I don't like that about jump. But if I have 806 sample size, what are my degrees of freedom for my interval or for my test? My degrees of freedom for my interval or my test are what now? 805. And you see it right there. It already did for you. Wow. It just does it for you right there. Automatically does it for you. So now we get to the two sample t, and we like to say the two sample, Alexa has said it perfectly. The two sample t's of degree of freedom, two sample t degrees of freedom are too complicated. You will not be solving the two sample t degrees of freedom on the test. You will not be solving the two sample t degrees of freedom on the test, because the two sample t degrees of freedom, if you work it by hand, are going to be, wait for it, the two sample t degrees of freedom are that. The two sample t degrees of freedom, say it with me, are what? The two sample t degrees of freedom. The one sample is n minus 1, and the two sample is what? To find the degrees of freedom, it's what? It's too complicated. It's too complex. The two sample t is too complex. Now you might say, well, how would we find it? Well, if we're doing this in statistics, first off, jump is just going to tell us the two sample t degrees of freedom, 128. There it is right there. It found it for us. But if we have to do it, great job. Right? Oh, I put it in. If we had to do it, we'd have to go over here. And we'd have to go to the applet, pull up the applet. Oh, it's over here. And so we'd enter in the mean for the sample size for the first group, sample size for the second group, standard deviation for first group, standard deviation for second group. There's the mean, the sample size, the standard deviations, and then the degrees of freedom. And there it is right there, 128.2926. And we do not, Jump's going to find it for you, but it's important to know what the degrees of freedom are, that you could go over to an applet like this to find it. All it's doing is solving the equation for you on the screen. I'm not going to solve that equation by hand. That equation right there is too complex. We just don't solve it by hand. Also, if you're wondering about my statistical software over here, the one that I use, if I were to have two vectors right here, I guess I could go and test these two vectors right here as though they're two samples. I think this will work. It's going to find the degrees of freedom for me, and there's the degrees of freedom right there. So just understanding that tells you the shape of the distribution. And I'm asking, is there a difference between the miles per gallon and horsepower of a car? And the answer is most definitely yes, by the interval and by the test right here. Where's the p-value? There's ridiculously low p-value, and there's the t-statistic, not the one for the interval, though. So understanding output will give you these degrees of freedom, but the degrees of freedom tells you yourself. Brian, I know, right? I was like, great. Oh, that's me. So the degrees of freedom for the two sample t when we're comparing two groups, categorical 2 level x versus a quantitative y we are measuring right here, then it's a too complex formula that we're just not going to do. Now, the chi-squared test of independence is one of my favorites because in this we are doing two categorical variables. What is the condition for two? What is it called? If we have two categorical variables, we have what kind of data? So if I'm talking about the chi-squared test of independence and we have two categorical variables, I'm talking about what kind of data? You say, oh, the chi-squared test of independence, we have count data. Great job, Priya, and great to see you, Priya, right here. Oh, we have count data. And what does it mean to have count data? Well, you're counting observations in each group. We can look at some of the tests we've been doing previously. We're trying to get a smaller one. Here we go. So I count, like I see right here, and it literally says count 148 people who are not in Greek life and on campus. What is another synonym for count that will be important to know when solving this? What is another synonym for count that will be important to know when solving this? Another synonym for count is what? Another synonym for count is what? How do we use it in formulas? Like if we're doing the chi-squared test, observed, exactly. It's that the counts are the observed. It's how many we see, which will be used for the observed minus expected squared over expected in the chi-squared test of independence for cell chi-squareds. We did a few of those earlier. Check it out. And so now with this data right here, you have to look and you have to say, Brian, that's a what by what. Leo, I'll try to do some new ones. I know Leo already knows the trick to this one. But what are the degrees of freedom? Who knows the degrees of freedom? We've tricked people. We've tricked. So when you do this, this one's a tricky one. I chose a tricky one to start right here. There are 4 degrees of freedom. We're throwing the 1,000 points because this is where we got to practice. We've been doing so well getting so many questions right, and the more we miss, the more we learn. So, because then we can see. Great job, Mary. Good to see you here. There are 1, 2 groups right there. What do we not count? What do we not count? We don't count the total columns. And there are 1, 2, 3, 4, 5 right here. And you don't count the total. Does that make sense? The totals are not used, so this is a 2 by 5. Hold up your hands, do it with me. 2 by 5. What's the formula? It's a 2 by 5. Is that right? No, it is that way. It's a 2 by 5. Good, Majed. Great to see you here. 1 times 4. 1 times 4. I like the... It's like...
I have returned.
Oh, I'm using my energy. I haven't drank my second cup of coffee. Drop finger on both hands. And you're actually doing the formula right here, which is row total. Oh my gosh. Rows minus 1. I was thinking of expecteds. Rows minus 1 times columns minus 1. And those are the degrees of freedom. So, epic energy. So the chi-squared test of independence is 2 categorical variables. So it's rows minus 1 times, and we do give this to you, columns minus 1. equals degrees of freedom. So let's see right here. Let's do another one. Let's try to find something a little bit more interesting. We did that one earlier, so a new one. Okay, so I'm going to try to find one we haven't done lately. Let's do this one right here. Okay. Oh my gosh. Sure. And actually, let me fix this data before we do it, because it should be ordinal also. Ordinal categorical variables are categorical variables that have an order to them. Shocking, right? The fun about this is real data, so it's pretty neat to see. Oh, Leo already... Is it... careful, Leo. I'm trying to think. I'm going to need to see it again. People are saying 12? Well, I guess... Is it? Is it not value ordered? Is it 12? Oh, no. Value order? Is it? Is it? I think it's... We're going to see here in a second. Making it look pretty. Okay, there we go. Okay. Careful. You're going to have to look very carefully at this. Look very carefully. It's not 12, I'm pretty certain. Yes. Kristen, how'd you do it? Kristen, how you do it? Priya, you got it. 1,000 points, everyone. Does everyone see it? Brian, that's a what by what? Brian, that's a 5 by 5. I'm trying to do more complicated ones, like ones with like small categories. Brian, that's a 5 by 5. Go right here. 5 by 5, drop 1. 4 times 4. And, you know, this goes with what we probably... So the degrees of freedom are 16. I think there were some smaller categories. I think it just made it a little bit easier when I put them in order, that you can see that this is a, like a, not a Likert scale, but it goes in order from very conservative to very liberal. There's 5 categories on each. A little bit easier to see when they're in order right there. No, the first one was just really poorly displayed. I think I canceled out of it. It's still the same display, but I made it ordinal data. So that way it actually changes the colors inside a jump when it's ordinal. It's like a heat map coloring. But this is much easier to see now that I've put them in the logical order we would think. Like, actually, I guess it'd be left and right. I don't know. I guess very generally. Oh, yeah. Yeah, because left is considered more liberal and right is considered more conservative. But when you think about this, does just this make sense with your world? Look at the individuals here who have an economic view that is very conservative. These individuals that say, I'm very conservative economically, and they are more likely to be very conservative or conservative socially. These people say, I'm very liberal over here economically, and then they're more likely to be very liberal or liberal on social issues. And just look at how the red right here, which is liberal, I guess, can we inverse heat map color this? Set colors. Oh, here we go. I have to do the whole heat map coloring myself? Give me a second. There you go. So now we've got it more accurately colored by ideology in America. Yeah, exactly. A little backwards for color. So I had to kind of do... I think you can have it set the gradient for you. But now if you look at this, the very liberal, associated usually with like left Democrat, shows up down over here, and we see more liberal views on the social issues for these categories. Where over here, for the very conservative, you see more very conservative views on those who are economically very conservative over here. You do have people who are very economically conservative, but are very socially liberal. You do have people, we got a liberal individual right here who is very conservative, There's at least one person right there who's very conservative. Yeah, pretty neat. Fun doing stuff like this. And you can see the categories down here and take a look at it. Now, do you think there's evidence of an association? Is the p-value for this test going to be high or low? What are your thoughts? This is a good advanced question. Then we'll do like one more topic of your choosings. Thank you, everyone, for being here. Do you think the p-value on this test will be high or low? And what does that mean? This is a little bit of an advanced question here. We've done degrees of freedom a lot on this. It's a 5 by 5, drop by 1, 4 times 4, 16. Do you think the p-value on this would be high or low? And then what does that mean? So this is a categorical relationship. We're analyzing to see if economic views are independent. It's going to be very low. It's going to be very low. Oh, yeah. No, it's tons of fun, Kristen, right? It's going to be super duper low. Because tell me, it looks like there is a what association here between someone's economics views and their social views. It looks like there's a very what association here, which is not likely by random chance. It looks like there is a very what, 5-letter word for very what association. Very what association. I would say there's a very strong association. Does that make sense? Very strong association. This is, yeah, that p-value is, there's 200 zeros or 199 zeros. It's 0.00. If I max out how many zeros I can write, actually, it's literally this. This is the p-value. I can just look at the character limit. You are about to see the p-value, and I have to write the next thing on. I think it was a 7. There's the p-value. It's basically 0. Strong as 6 letters. Oh, did I say 5? I can't spell. I do know how to solve p-values though. See, there we go. It's more important to my discipline. Super duper significant, crazy significant, right? Like if someone told you, I don't think there's an association. What would you say to someone who said, I don't think there's an association between somebody's views on economic issues and social issues? Like, I think it's just random. Like, you could be liberal on economic issues and it would tell you nothing about someone's views on social issues. What would you say to them? You'd say, I reject that. That's a ridiculous idea. There's strong evidence. And they're saying, wait, are you telling me you have to be this if you're this? You're saying, no, there's just an association. You generally see people with more liberal views on one generally having more liberal views or more conservative views having more conservative views. There's an association. It doesn't mean you have to be anything. It just means you generally see this trend in the data and it's not random. There's an association we see right here between people's views. There's evidence for the alternative. There's lots of evidence at the ridiculous significance level, at the winning the lottery, but it doesn't cause, great job right there, Priya right there, it doesn't cause people. We can't say you will do this, or it causes you, or we've proven this. We don't use those words in statistics. We never, if you see cause and effect. Let's see, any last questions? So I think we covered all the degrees of freedom. Good kind of talk. That's the degrees of freedom for the chi-squared test of independence. Let's go back to the main screen. Well, we've done a 2.5-hour review today, and we did all of conference roles, all of testing. Maybe some calculation. What kind of calculations do you want to do, Leo? You pick. Do another segment right here. You pick what kind of calculations, like t-test calculations. I'm trying to think like of the word problems on the test. Where's that? Is that the keyboard? Keyboard wrecking my green screen. Any calculations? What is the majority of the exam over? The chapters have covered. always write down every Canvas content you can. We'll maybe do that tomorrow. And yeah, we should play it again sometime. Play it again sometime here. Can we do? Yeah, I think tools and techniques. Leo, does that sound good? I think tools and techniques might be a great thing to end on today. Like tools and techniques. So I think tools and techniques are great because we haven't done a ton of those. That's a great suggestion. Can we go over exam formula sheet? Yeah, I think we'll try to do that. Yeah, get enough time right here. I think we can. Let's do that. Tools and techniques. Okay, so the tools and techniques. What are tools and techniques questions? Sure. That's how you spell it. Tools and techniques questions. Questions where you have to know what graphics or tests we would use from this class. So that's what a tools and techniques question is. It's like, do you know how to apply what you've been learning in future instances? Well, I'm just kind of scattered out. That's kind of everything. What bind is it? Oh, there's Control C, I think, does it. No, I don't know. I don't know. Rephrase it, Leo. I'm sorry, my brain went. I don't know if I can, Majed. That's a good question, Majed. I might be able to. If I did, other instructors would need to make it too. Like if I made some special thing, then we'd need to make it for all sections. So that way no one's like Control Shift E. Oh, good answers right there. Wait. Control E. There it is. Control L. There we go. Highlight over there. There we go. Okay. So with the tools and techniques, I'll put the new segment right here. With the tools and techniques, let's talk about tools and techniques. Tools and techniques are going to be questions where you have to know what graphics or tests we would use from the class. And so probably one of the best things to write down if you don't have a screenshot of this is the following. This is a majority of what we've done in the class, telling you the combinations. Like, what does it mean that the histogram is over there by itself? Like, it has a y variable right there, and then there's nothing on the x-axis. So what does that mean about histograms or box plots or stem and leaves? Like, to understand what this graphic is showing you right now, Leo's got some credits. It's a quantitative Y, right? Like, if you want to analyze GPA, or if you want to analyze someone's height, not at the same time, but if you want to analyze a quantitative variable, you could do it with histogram, box plot, stem and leaf, dot plot. But additionally, we should also know what tests we would do. So I should probably need to remake this graphic right here and then do it for tests. I might have to like edit the screen, but I should have a graphic from my board of the tests. Chelsea wrote this all out for me, so my handwriting would never look this pretty. And so what you notice right here is what do we have for bivariate categorical? Bivariate categorical, so try to use the graphic right now and tell me, bivariate categorical. Oh, nice. Someone has it already. Leo. That's good stuff. Put it out there. Great job, Kristen, right there. Bivariate categorical is mosaic plot, contingency table. We could do stacked bar charts for visualizations or side-by-side pie charts. Not a big fan. These are kind of put in order of importance. So you can see like the big ones we would use, like bar charts, pie charts for categorical data, or side-by-side box plots, stacked histograms. Oh, the bottom ones. Yeah, we don't look at those. It's just generally not as important the lower you go on these right here. Okay. So the other things, so you have graphics we just saw, and you have tests, which we talked about earlier. So let's think about this. We're going to come up here with 5 questions. Someone wants to display who is more likely to own a pet. They have data from students who live on campus and students who live off campus, and whether or not they own a pet. So we're doing some graphic questions. So what is the thing doing there? Thank you. Didn't like that. Maybe keep those answers rolling in. Maybe. And then we're going to find how we got to keep answering. Someone wants to display who owns more pets, and how many pets they own. Okay. And then, Leo's going outside the box right there. Someone wants, or a company Company is interested in where their sales are happening. They have data from each location of sales and want to display this to their stockholders. A company is wondering if their net revenue has increased this year, and they want to make a graphic of daily net revenue and display it. Company is comparing sales from last year to this year. Daily sales. It's comparing daily sales from last year to this year, and wants to create a graphic displaying it. Last but not least, the company wants to compare each day. Company wants to compare today's sales to last year's sales. Each day will be compared to see if there is a trend in the data. That's a tough one. I'm trying to have you think through these. A little bit tougher here. Okay, so let's think through the first one right here. Someone wants to display who is more likely to own a pet. So what should you start doing with tools and techniques? How do we solve these? I think we got a lot of right answers in the chat. Great job. Tons of right answers right now. Majed, that is right. I think all these are right answers. I don't know if I see any wrong ones yet. So if you've been answering them correctly. How are you solving these? What is the key to solving these? What is the key to solving these? How are you doing this? If people are watching this, like, how do you know this? Right there, Priya's pointing out we want to figure out if it's categorical or quantitative, if it's bivariate or not. So we need to go here to the question and decode it and say, okay, we'll put right here this means categorical. And we'll put right here, this means quantitative. Okay, so the first question says, someone wants to know who is more likely to own a pet. Students who live on campus or off campus, and whether or not they own a pet. So we have on or off campus and whether or not they own a pet. So students who live on or off campus and whether or not they own a pet. So how many variables are there? So we have, do you live on or off campus? That's one question I'll ask you. And then we have, do you own a pet? So now the display for this probably your number one is going to be a mosaic plot. So, hey, MG, great to see you here. 100 points, MG, right there. So the display for this is going to be a mosaic plot. Two cats right there, two categorical variables. So two categorical variables are being used right here. Any of the answers, mosaic plot, contingency table, stacked bar charts, side-by-side pie charts. Once again, I would go in order of the variables right here. We're looking at the one I'm in front of. So mosaic plot, contingency table, those are your best bets. The other ones are possible. Not a big fan of putting those on the test for the tools and techniques. These are multiple choice, but we're going to solve them without the multiple choice options because then we're just seeing the solve methods. So that's the first one right there. Remember, we're doing blue for categorical and green, yellow for quantitative. So now we have a student wants to display who owns more pets. They have data on students who live on or off campus. So what is this going to be? Saba said ring charts. No, we don't like ring charts right here. Homer Simpson. How many pets they own? What's the deal? What's the deal with how many pets they own? Let's see. Follow along right here. I think people got this one also. What's the deal with how many pets they own? Oh, dude, someone have 300. Oh, yeah. Leo's at the Leo and Troy level. Quantitative. It's a quantity of pets that you own. I own 2. I live off campus, if you didn't know. So, probably... what do we have right here? What do we have? We have side-by-side box plots as best as Brian can draw. Side-by-side box plots. Does that make sense? Side-by-side box plots. I think we have a Priya level too and got a Troy and Leo level. Side-by-side box plots. Thank you to everyone, my people who've been here. Priya's in the club, in the Troy. She's the leader of the club right now. I know, right? Thank you to everyone who hangs out and gets tons of hours and tons of watch time and tons of fun. So there we go right there. Next one. A company is interested in where their sales are happening. They have data from each location. How many variables? Yeah, Priya, let's do that right here. We'll do that. I'll do it here after this question. Remind me, Priya. We'll get you a level right here. People will be wondering next semester who these levels are. They'll be like, whoo, 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 whoo. Goes to the lore of Stat 201. If you want it to be your name, I can do that. Or if you want something, we have an Epic Wolf level from someone. What kind of thing are we dealing with right here? What kind of data? You're figuring that out right now. What kind of data? And then we're going to draw the graphic of it over there. This was side-by-side box plots. It could be stacked histograms, side-by-side bar charts, box plots. Oh my gosh, I can't speak. You're down here in the bottom left right here because it's a categorical X and a quantitative Y. So what kind of thing are we dealing with right here? Oh, with the, what kind of data are we dealing with right here? Who knows? I already saw some right answers to this, but what kind of data are we dealing with question 3? I already saw right answers, but the key to solving these is, once again, finding the data. Great job, Kristen, right there. One categorical variable. It's one categorical for this one, and it's where are their sales happening. So each location, think like location A, location B, location of sale, like was it at, store A, store B? So that would be count. It's not bivariate count data, but it's just one, like where did the sales happen? So that's a category, like what store was the sale in? Does that make sense? But how much were the sales is quantitative. Does that make sense, Leo? Like how much, which we're going to kind of get into in the bottom right here. How much were the sales is quantitative. But good to hear, Thomas. But the other thing of like where did our sales happen, like what was the store, is a category. Like it happened at store A or store B. That's a category right there. So the answer for this one is going to be what? Repeat the answers again. Any answers you have. Once again, the graphic over here is going to be a big help for possible answers. We know we have one categorical variable. Pause the screen here. Take a look. One categorical variable. So what would be some possible answers over here, which we're going to draw on the side then? Bar chart, pie chart. You can make a pie chart your bars, bar chart your pies. Good stuff right there. Pareto, which is the bar chart put in order. So all those answers right here are very possible. So we'd get different bars. Now that's not a histogram, because this is like store A, store B, store C, store D. Histograms are quantitative and have a quantitative axis. So that's a bar chart right there. Histograms are quantitative. Great job. A company is wondering if their net revenue has increased this year, then they want to make a graph. So they're wondering about the net revenue this year. They just want to look at net revenue this year. How much revenue? And they want to look at daily net revenue, daily revenue, or daily net revenue. Does Pareto only work for ordinal? Pareto is just for categorical variables, and it's not for ordinal though. It can be for ordinal. It's just for any categorical variable where the bars are put in order. So this could be, it would have to be reversed. If the bars go in order, you've made a Pareto. Paretos are bar charts that have been put in order. So any bar chart, regardless of ordinal or nominal, Kristen, could be Pareto. Pareto just means put them in order. Any bar chart could be put in order. So great question, Kristen. 100 points. Any bar chart could be put in order. And thus, then it would be a Pareto. So that's bar charts put in order are Paretos, most to least. So what is this one going to be right here? What kind of variable? Yes, we're going to have R review, then SI review, I think, after, right? What kind of data are we dealing with? This one, I tried to make these a little tough. Tried to make these a little bit difficult. What kind of data are we dealing with for this one? Who knows our data for this one? Company is wondering if their daily net revenue has increased. So they're going to look at One quantitative. Great job right there, Kristen. One quantitative. So they're looking at daily net revenue. They're just looking at their daily net revenue. So what answer do you think would be great right here? If they're looking at daily net revenue, we've identified that as a quantitative. Blue is for quantitative. Great job, Majed, right there. And so what should we display it with? I'm going to let you see the graphic screen again. Histogram, Leo, you're right. That's a histogram, box plot, stem and leaf, dot plot, any of those, dot plot. And that's going to have a quantitative scale to it. The histogram does have a quantitative x-axis. A company is comparing daily sales from last year to this year and wants to create a graphic displaying it. Now, these could be worded a little bit better. So they're looking at daily sales last year to daily sales this year. And I went back and I did another side-by-side box plot. I would word these a little bit better. I think the test questions are worded perfectly great. These last two, I don't love them as test question right now. So we're looking at daily sales, which is quantitative, and then they want to compare last year to this year. So that's two groups. They're comparing two groups. We're starting at 10. Double check. Double check the time. It's posted on YouTube. It's in the morning, in like 10 or 11 or something, or maybe noon. I don't remember. Kristen, you do know the test. That is correct. So we have like the same sort of graphic from earlier, where we're comparing last year to this year. So 11 a.m. Thank you, Priya, right there. 11 a.m. it looks like. 11 a.m. Knoxville time. That'll be 10 my time. The company wants to compare sales from today to sales last year. Each day will be compared to see if there's a trend in the data. Thank you. Oh, Terry said it right there. It's going to be noon. There we go. That's better. It is noon, apparently. So now a company wants to compare like this year's sales to last year's sales, but they're doing it as like, let's compare each data point. I don't love the way this one's written. No worries, Priya. Terry writes better questions than this. This question would not reach the Terry level and go over there right there. So this one right here, we're comparing, but we're now looking at a one-by-one comparison. So think of this. If we have, I'll probably help solve this one. Today's sales and last year's sales, that's the answer to the question. So we have a vector of today's sales. We have a vector of last year's sales. So think about that. What have I just told you? We'll wait. Go by the color coding. We have today's sale. Oh my gosh, what have I done? Did I reverse these? Oh no. Daily sales. Oh no. There we go. Two quantitative variables. Sorry about that. I reversed it at the end. Thank you, Priya. I appreciate that. I made a reverse right there. There you go. Terry just rocked. Terry, 1,000 points for Terry right there in the chat, helping out. So since we have two quantitative variables right here, and we want to look at, is there a trend with sales? Like, is there some sort of linear trend? What do you think we should do with two quantitative variables? I should like not reset Terry's points. Like, Terry. There's a button to reset everyone's points that I always use. Make sure to mark down your points. Well, I download the CSV anyways. Oh, thank you, Kristen. So what do you think we would use to display this? Scatter plot. So two quantitative variables is a scatter plot right here. And so that would be, so when you have two quantitative variables, a scatter plot right there. Excellent stuff. 30. Just get me the 3090 Ti and I'll be happy. Talking some graphics cards in the chat. Well, that's very nice of you, Leo. Chat, you destroyed me. Okay. Let's take everything we have right here. And now, instead of doing the instead of doing the graphics, let's talk about the test we would do. So now everything we have right here flows. If we know the graphic, you might be looking at a lot of these and be able to quickly figure it out. I think you should be able to quickly figure out a lot of the tests from this like this. We don't have everything listed. I'll thank you. Everyone's so nice today. So the first one right there, what do you see? You see that we've already decided on a mosaic plot, right? So what's the first one right here? You see we've already decided on a mosaic plot. We have two categorical variables, which leads to count data. So what are you thinking is the test you would use? So think of the test now. What test use? Use what test? And I want to say this. It's really thanks to people like Terry. Just I could name so many people, but I just want to give shout outs to Terry, who's here right now, because Terry does so much work in the background. I can't tell you how much it is that like, if you're saying thanks to me, you're saying thanks to everyone I work with too, because that's not just like, oh, thank you, it's everyone I work with. No, like, no way could I do this without the leadership of Terry Higgins, who is the coordinator of Stat 201, who's always like, we have a like we've met like 3 or 4 times this semester. We make sure everything's going smoothly. He's always updating things, fixing problems if we have them. So a lot of the it can be Brian and Terry giving a high five right there, being like, like, or like we do like the predator handshake. I'm sure Terry knows about that. I'll be like, Terry, you'd be like, Brian, and then like this one takes a picture and that's the statue. So really thank you, Terry. Like sometimes, especially, this is a quick aside, like shout outs to both Dr. Lou's. There was one semester, it was when COVID hit, that Dr. Lou, Charles Lou, did so much work for 474. Like I teach sometimes like 3 or 4 preps. Like right now I'm doing 201, 324, 75. And it's a team effort. And I try to remind myself of that sometimes when I'm like doing a whole lot. Sometimes I'm like, okay, I don't need to do everything. Like I have people who I work with who are awesome. And I still want to help out. I want to do my fair share of the work. But sometimes I remind myself that I don't have to do everything. And that gives me a little less anxiety. And so I'm really lucky. Like the department, I think, is great. The whole business analytics. Don't worry. And we're business analytics and stats. So anyways, huge shout outs there to everyone. And Dr. Galbraith, our leadership, who's absolutely awesome, who met with me and was like, hey, I hear you do this YouTube thing. Yeah, we have a super strong department. I dare say we're the best. I dare say Haslam College of Business is the best. I dare to say such things. Oh, let's put a timestamp in here and let's do tools and techniques. We did graphics. And we'll do tools and techniques on the tests. So tools and techniques, we just did graphics. Now we're putting a timestamp for tools and techniques tests. Okay, so we need to know what test we would use now. So when we think about what test to use, thank you so much, Kristen, right there. When we think about what test to use, it comes down to the what's of what we're asking. We've already highlighted this. Check out the first part we just did. It comes down to the what's we are using to figure out the test. It comes down to the what we are using to figure out what test we have here. And we'll write down a cheat sheet here in a second, the variables, right? So let's think about this. Can you just name off some tests for me? Like, T, Z. What do you think? Name some tests for me, and then I'll tell you what variables go with it. Name some tests for me, and then I'll be like, oh, this. T-test. T-test. That's a good one to start. We're just making a test bank of tests. So there's a T-test. So tests you've learned. T-test. Class squared. Baseball squared? Nope. It's 5 letters, right? 2 sample t-test. And proportion z. Prop z. 1 proportion z. Oh, I'll spell it out. Proportion z. Am I missing anything? You could do goodness of fit. I'm going to put that down a little bit here. Goodness of fit. That is a test. 100 points, Kristen. Goodness of fit is a test for the normality of a distribution, or the generally use it for the normal, but you could do a goodness of fit for a Cauchy or whatever distribution, or a inverse binomial. I don't know. Inverse geometric. Goodness of fit. That is a test. Don't see a lot of tools and techniques. I don't know if we ever wrote one that uses that one as the answer. Should put it on here though. Little bit of a special one right there. Not commonly used in the tools and techniques test question bank, but worth knowing. We're missing decision trees. Those aren't really a test. Also, I'd say we're missing. Oh, and then we're missing another. We're missing one more important one we just talked about here. Scatter plots need what? Scatter plots need what? Scatter plots need what? Scatter plot needs a what combination or a what analysis that will lead to residuals. And what analysis are we doing? So if you do QQ straight enough, no outliers, you are doing what sort of analysis? It's the last one we did right here. Oh, you're doing regression. Regression, Kristen, great job right there. You're doing regression. Yep, you're doing regression. Okay, so you'll notice something interesting as we do this. I want you to notice what happens as we do this. Let's say we have a categorical variable. Let's say we have a categorical variable. If we have a categorical variable, if we have a categorical variable, we're doing what? If we have a categorical variable, we're doing what? We're testing the proportions, right? Does that make sense? So 1 prop z. The proportions are for the categorical. But as soon as you switch to t, you got to think what's. As soon as you switch to t's, now I know don't say the variable type yet, but you got to think Mr. T is this. You got to think mean. And if we're dealing with means, we have what kind of data? So as soon as you switch to t, you think mean, and you're dealing with what kind of data? Quantitative now, because the only way to get means are for quantitative data. So now you're over in quantitative. Now you'll say, well, wait, this is a 2-sample t. If we have here a 2-sample t, you think, wait, I now have still quantitative data, and that's the y is going to be quantitative. Sure, why not? The y is going to be quantitative, but now we need a categorical x. So the x over here is going to be categorical. Does this make sense to everybody? The x is going to be categorical. Really? The x is going to be categorical. And that is because we're looking at the means for the two groups right here. We're comparing the means for the two groups. So it's a quantitative y, and you can see this if you look at the analysis of it. Anytime we do the 2-sample t-test, we didn't do one there. We're doing all the way back here. You're looking at a quantitative y like high school GPA and a categorical x that is 2 levels. So you're seeing a side-by-side dot plot of sorts. We could put on the side-by-side box plots there, which is the graphical display, but this is a 2-sample t-test, and that is testing the difference between the two means. Great job right there, Leo. This is testing the difference between the two means because you're looking at the mean for the one group versus the mean for the other. So we're still doing the t part of it. So we should mention that the t's are always the quantitative aspect of it. So this whole idea of this right here, the t goes with the quantitative aspect of it. So the t's are for quantitative. So the t right there, when you're doing two means, you're doing the 2-sample t-test, looking at the difference between them, as Leo's pointed out. Now, the chi-squared test of independence has a condition known as this data, and then the way to meet that condition is what? The chi-squared test of independence has a condition right there, and Leo knows right there, already doing it. Great job, Leo. The chi-squared test of independence has a condition where we have two categorical variables. Wow. 2 categorical variables, and there's a categorical y and a categorical x. So we have 2 categorical variables when we're doing the chi-squared test of independence. And then once again, we always put the word independent between when we do the phrasing. Simple enough. Someone's economic view is what of their social view? Just finish. Tell me what the sentence here. The null hypothesis for this is someone's economic view is what of their social view. You like say, oh, the null hypothesis states that someone's economic view is what of their social view? Independent. Remember, literally just put the word independent between these. It's the easiest way to write the null hypothesis is to just go here and say independent. That's all we do. And the alternative would be not independent. So the null is their independent, and the alternative would be not independent. You can say other things like dependent or associated. There's other ways to do it. Mike Pearson does a good job reviewing those. And we reject the null hypothesis exactly for that one especially. Now, regression is a little bit different. And we're going to have to remove this one right here. So regression, when we do regression, what do we do? What do we do? What is our thing right here? What did we used to say? You don't have to know these conditions, but what did we used to say? What did we used to say? In regression, only favors here. In regression, we say what? QQ straight enough, no outliers. The whole straight enough deals with that. We're doing a what with these variables. The whole straight enough deals with we're putting in a what for these variables. It's not on the exam, the idea of it. The idea of it and when would you use it. So we're not going to be solving it. The whole idea of QQ, two quantitative variables, straight enough, no outliers. The straight enough means we're putting a what onto the data. The reason we want it to be straight enough is because in regression, we fit a what to the data. Look at the green thing right there. A line. So we want it to be a straight enough relationship. So QQ stands for two quantitative variables, which is the condition for regression. You're not meant to understand like all the coefficients and all the extra stuff. You're meant to know when to use it. That's the point of tools and techniques. So we would say something like, if somebody wanted to analyze the age of someone in their high school GPA, what graphic would this make? So just look right here. And first off, just tell me what graphic would this make? So if someone wants to analyze the age, Jet, great to see you too. Let's say they want to analyze age and high school GPA. And you've got some hints, by the way, Jump is showing it. Someone's age, how old they are, how many years do you have, quantitative, your high school GPA, and Leo has right there a scatter plot, and you see it right here. And then if they want to do like a statistical test, what kind of statistical test would they use right here? What kind of statistical test would they use? The statistical test or technique they would use is what? None? Well, it's two quantitative variables, right? Regression. Does that make sense? So they could use regression right here. Line of best fit, which is regression. They could also use, and we should say this, let's put a note right here. What also is the same, not the same thing, but is built upon this. Let's put same for what? Like you would do the same thing right here for this. I guess we could do it right here. What also, it's not the exact same thing as regression, but it's going to be the same sort of format. Because regression talks about the linear relationship, and this is the linear relationship too. So what other concept did we have for like linear relationships and the strength of the linear relationship is the what of two values. They're what? Which only applies to two quantitative things. It has the first three conditions of regression on it. This is if we wanted to look at the what between two things. The linear relationship. If we wanted to see the correlation, Leo, great job right there. The correlation, yep. So you can look at the correlation. Once again, we're not really finding values with tools and techniques. The correlation could be easily found by taking the square root of r squared. The correlation is going to be negative right here. So you can find out the correlation from r squared. We're not doing that right now. That's not a tools and techniques type thing, so I'm not going to do it. It's test 2 right there. But correlation is a concept related to this, which can be done with two quantitative variables, so it's important we know that. Now, decision trees are going to kind of break from the way we're formatting this because they're a little bit special, a little bit different from this combination. But I want you to notice this right here. Look at how we have the univariate displays. We have univariate, univariate. Then we have bivariate. And what do you notice right here? You basically have all the combinations of like categorical quantitative variables. There is one, if you are wondering, which is not on the test. And what tool do you think you have not learned that we've crossed out here, which would be a categorical Y, quantitative X, and it would be the proper tool to use, which is a sneak peek. If you take 320, we will talk about that one, and we will use it a lot throughout the remainder of 320. A tool to use a categorical Y and a quantitative X, or any X's, would be logistic regression. And that's a story for another day. So that is the missing combination that we don't have on this screen. I don't want to put it here for people watching for Stat 1, but that's a kind of neat preview of what's to come. We do have a way of handling that. But decision trees have a special space in what we use. Decision trees are when we have how many Ys. So how many Y variables? So kind of deceptive right here. But a decision tree, and we'll kind of go, we're going to do a little off thing color coding. 1Y. This is our like off thing right here, because decision trees are like 1Y tons of X's. So this doesn't really follow. It can be anything. You can choose a quantitative, you can choose a categorical. 1Y and then tons of X's. You just toss in all your X's and it does the work for you. So there are questions that could be written like, Brian wants to figure out students' performances in Stat 201 and predict their grades. So that's 1Y. Boom. Doesn't matter. Categorical, quantitative, rock nose.
It doesn't matter.
Brian has collected 50 question survey on his students. What tools say it? In the chat, Brian is trying to predict the grades of his students and has collected a 50 question survey asking them things about like how long they study, all these different things. What tool should Brian use to analyze that data? How should Brian analyze that data? Brian has collected, he wants to understand the grades of his students, and he's collected 50 different questions on them. You never know. You never know. We have meetings about curves. You never know, Leo. Keep your fingers crossed throughout all exam period. Gotta be like, I will not uncross my fingers till a curve happens. You never know. Not chi-squared. So chi-squared is for a bivariate. Good job, Majed, right there. Chi-squared is bivariate, but decision trees, no worries, and great work right there. Decision trees, Brian wants to predict the grades of his students, and he asked like 50 questions. They can be quantitative, categorical questions, anything. Decision trees handle tons of data. To review how a decision tree works again, we simply go over here to the predictive modeling partition. We drop in the variable of interest. We'll remove out these categoricals. So you can take all these variables. I think I still have in favorite phone app. You don't need to know this kind of stuff because we're not talking how to do it. I'll just predict honors program. Now, let's go here. We'll predict if someone's born in, sure, why not? I already deleted it. We'll predict high school GPA. And now you can see we're making a model. I'm not trying to make a good one here, but you just put in all your X's, and then we're predicting high school GPA right here. Exactly. So kind of to find relationships, because remember, correlation is only between two quantitative variables. So decision trees allow us to take one Y we're trying to understand, and it could be categorical, it could be quantitative. But what's the key to knowing? Just doing a super quick one here. I'm going to leave in the identifiers for the moment. The wrong button. The key about a decision tree is it's one Y variable and what? The key about a decision tree is it's one Y variable and what? It's one Y variable and what? The key about a decision tree is it's one Y variable and what? The key about a decision tree is it's one Y variable and tons of X's. Now, don't worry, I didn't do the proper theory behind it. I left in the identifiers, but we can see here that it could be a quantitative Y or a categorical Y, and then there's going to be lots of X's, and I did make a theoretical mistake. Don't worry about it. So the key on a decision tree is one Y, lots of X's. That's the way to distinguish it. Pivot charts, I don't know. Let's put it right here. Univariate. It's just generally a decent idea for all. I don't know if we have any answers that are pivot charts, but it's just generally a decent idea. It's like an okay idea. Goodness of fit test. Use test normality of quantitative. So these are kind of the unique ones down here. Goodness of fit test is when we go to a distribution and we say, is this data normal? So we're using it, a goodness of fit. It looks kind of normal, but it's got a little bit of skew to it. So we go to the continuous fit normal. We put the normal curve on top of it, and then we ask, is this normal curve, the reason it's called goodness of fit, is we're saying, is that curve a good fit? And you see how it has problems? So since it has problems, it's probably going to have a low p-value. Goodness of fit, and p-value is low, so we reject normality. I don't really see it, hence I'm doing this a little bit fast because I don't see these being big. I don't think we have, I don't know if we do. We could, it's fair game, but the main ones up here were done first. This is really your bread and butter of what is likely to be seen. The lower ones are less likely. Like decision tree is still in this boundary. The boundary of what I don't think, let's put here less likely. So these are less likely right here. There we go. Look at that. Kristen, I'm learning things. There we go. So there's the tests we've learned. And now let's use this knowledge right here to do the tests. Did we just reverse color code? Sad day. So remember, categorical is blue in these examples. Quantitative is yellow. I just reversed color code. Sorry, we're on hour 3 right now. Okay, so the first one right here is 2 categorical variables because we're looking at if a student is on or off campus and whether or not they own a pet. So what's that going to be? Student is on or off campus and whether or not they own a pet, what's that going to be? On or off campus and whether or not you own a pet. On or off campus and whether or not you own a pet. Yeah, we'll probably end after this one. I'll get some more coffee and I'm going to go to the stores and such today. 2 categorical variables. So what do we use for 2 categorical variables? 2 categorical variables means we are using, so if you wrote them down, what are we doing? We got a mosaic plot. So what test are we doing? What test are we doing right here? Let me put that in like, what test are we doing? I'm trying to draw your attention to it. What test are we doing? That's the big question of the day. What test question are we? Oh, wait. What test? Used. Chi-squared. The chi-squared. 2 categorical variables is chi-squared. No worries, we're doing practice right here. Chi-squared. Okay. Next one, we have a categorical x and a quantitative y. You can see the categorical right there. It's this graphic we're talking about. So what test would be used here to compare how many pets people own on average on or off campus? So we're saying let's compare how many pets people own on or off campus. Think about what we're doing. We're comparing a quantitative measure, and we're comparing 2 groups. So those are the hints. The 2 sample t. So this is 2 samp t. Because 2 sample, because there's 2 groups, and t because we're comparing a quantitative metric on them. Next, we have the locations of sales. So maybe we want to see if like one of our locations is getting over 50% of sales. Like that's how it would be worded. It would say something like, we want to see if location A gets over 50% of the sales. So now we're doing locations and sales, which is categorical. I think Kristen's on the right track. Yep, it's going to be the 1 prop Z. 1 proportion, known as 1 proportion, we wrote out in full terms. And that's because there's 1 categorical variable right there, the 1 proportion Z. We don't have tons of X's for this one. There's just 1 categorical variable. There's no decision trees on this practice sheet right here. Oh, sorry. I'm sorry. I did reverse the color coding between the 2. I feel so bad about that. A little afraid to go in and reverse it all now, lest it made an error. Look right here. This is a quantitative response. Thank you, Leo, right there. This is a quantitative response right here. Yellow in this instance is quantitative. So what would we use right here to analyze the sales of a company? This is quantitative right here. Sorry, Kristen. They're taking down my statue as we speak. They're leaving the Terry portion up, but the Brian portion's gone. So this would be a t-test because Mr. T is mean if you're doing drugs. The t-test right here. That's the t-test. The next one, if you look at it, looks like a previous thing we did where I did my little sketch of it, where we're going to compare this year's sales to last year's sales. So the daily sales are quantitative and this year and last year. And so what would this be? What would this be right here? We're comparing this year's sales to last year's sales, the 2 sample t-test. Remember, t because the y variable is quantitative, Mr. T. And last but not least, we have comparing this year's sales to last year's sales, see if there's a relationship, like height and weight, two quantitative variables. Name both things off we could use right here, and that'll do it. We'll take a break, probably be back tomorrow morning, and then we'll do Sunday. Lots of practice right here. So what would we do right here? We're going to try to do different things in every video. Regression or correlation. Great job, Leo. Let's end with a big 2,000 points. Thank you so much, everyone, for tuning in. We're going to head off in a second. Regression or correlation. The number one thing, if you're watching this in the future, you're welcome, Leo. If you're watching this in the future, feel free to join in. Feel free to practice. A lot of people here, if you are free to do this, test 2 was super hard. I want people to know this. Who here in the chat is happy with their test 2 grade? I know you're free to post it. You're free to say it. But I know a lot of people who are here, who work through these, who it's all about the practice. It's all about answering the questions. Leo, great job right there. It's all about answering the questions and practicing. If you're watching this in the future, though, don't worry. You can practice by pausing the video. We got a thing in the second class. We bully exams. Don't worry, Majed. We're going to try to work this out. Yay! Lucy. We got to throw out more points for Lucy being here. Another 2,000 points. Random Lucy swings by right here. Lucy, so good to... I think I saw your stuff on LinkedIn. I think I see a lot on LinkedIn. I'm trying to catch up with the semester ends. But thank you so much, Lucy, who I think started in 320 and all that. And... Lucy, we've met. I think you started taking my classes right when COVID hit. All the craziness, right? But I don't know. Either which way, Lucy, keep it up. And Dwight's here. Everyone's here. Oh my gosh. Let's end off with a Smash Bros. Everyone's here. Dwight's here and everyone. Well, Lucy, I'm trying to plan out some stuff. Dwight and Terry can hear it. We're trying to maybe plan in a Brian visit to UT at the start of next semester. We're going to end here with a little Smash Bros. Let's end off with Smash Bros. Which way is it? The mic's that way, right? Dab on that exam. I blocked the thing. I don't know what's going on. Thank you to everybody. We're here to have some fun. No, we broke everything. You never know what we're gonna do. You got this. Dabbing's old news these days. Now we bully the exam. Bully McGuire. Shout outs to Spider-Man. We gotta update you on some modern dance moves. It's only like, 4 years old. My friend Logan and his brother Jake told me it was cool. I think they were messing with me, though. With that, everyone, we'll be back here next time. Don't be sad. See you probably tomorrow morning. Bye, everybody. Can you do a double dab? Maybe next time. Maybe Saturday review. Swing on by.